Right now, the light reaching your eyes from the nearest star beyond our sun has been traveling for 4 years, 4 months, and roughly 22 days. That star is called Proxima Centauri. It sits at a distance of approximately 24.9 trillion miles from where you are sitting. If you boarded the fastest spacecraft humanity has ever launched, the Parker Solar Probe, which reached a peak velocity of roughly 430,000 miles per hour during its closest approach to the Sun, and aimed it directly at Proxima Centauri, you would arrive in approximately 6500 years. Civilizations would rise and collapse in the time it would take your great-grandchildren's great-grandchildren's great-grandchildren to complete that journey. And Proxima Centauri is, by cosmic standards, our immediate neighbor. It is the house next door. But here is what most people get wrong when they hear this. They assume the problem is one of speed, that we simply lack the technology to go faster. That given enough time, enough funding, enough engineering, genius humanity will eventually build a ship fast enough to cross that distance in a reasonable human lifetime. They imagine the interstellar void as a challenge waiting to be solved the way the Atlantic Ocean was once a challenge, and then someone built a better ship. The real situation is far more disturbing than that, because the barrier standing between us and the stars is not technological. It is not a wall we lack the tools to breach. It is woven into the fabric of space and time itself at a level so fundamental that the very concept of going faster dissolves into contradiction when you examine it carefully enough. The cosmic speed limit, 29979, 2 kilometers per second, the speed at which light travels through a vacuum, does not represent the fastest speed a clever engineer has yet achieved. It represents the maximum rate at which any influence, any information, any physical object possessing mass can propagate through the universe. It is a structural feature of reality, not a record, not a ceiling, a definition. And yet, in 1994, a physicist named Miguel Alcubierre discovered something extraordinary buried inside the mathematics of Albert Einstein's own gravitational theory. Not a way to break the speed limit, not a loophole in the traditional sense, something stranger and more unsettling than either. A class of mathematical solutions describing geometries of space and time that would carry a spacecraft across interstellar distances at effective velocities exceeding light without violating a single equation in Einstein's framework. The mathematics was clean, the derivation was rigorous. General relativity, the most precisely tested theory in the history of physics, accepted these solutions without objection. The universe, it turned out, had a different opinion. What followed that 1994 paper was 3 decades of theoretical investigation, revealing something profound about the architecture of physical reality. Every attempt to make these mathematical geometries physically realizable encountered new barriers. Remove one obstacle and 2 more appeared in its place. Solve the energy problem and the control problem emerged. Address the control problem and the causality problem materialized. Each layer of constraint connected to the others through principles that became visible only in the attempt to circumvent them. The universe was not guarding its speed limit with a single wall. It was guarding it with a network of interlocking constraints, each one independently capable of forbidding faster than light travel, all of them reinforcing each other in ways that grew more apparent the harder physicists pushed. This is the story of what that investigation revealed. If you are someone who finds wonder in the architecture of the impossible, in what the universe forbids and why it forbids it, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue. Get yourself comfortable. We are going to travel to the edge of what physics permits. Let's begin. To understand why the Alcubierre discovery matters, why it was simultaneously so promising and so devastating, you first need to understand the barrier it appeared to circumvent. And that means understanding something that sounds simple and turns out to be one of the most philosophically strange facts about physical reality. Nothing moves faster than light. Not because light is particularly fast, though it is. Not because our engines are insufficiently powerful, though they are. But because the concept of motion faster than light contains hidden contradictions that dissolve into incoherence the moment you examine them carefully. The speed limit is not a record waiting to be broken. It is a consequence of how space and time relate to each other. Remove it, and you do not get a faster universe. You get a universe without coherent causality. The story begins in 1905 with a 26-year-old patent clerk in Bern, Switzerland, working through a problem that had troubled physicists for decades. His name was Albert Einstein, and he was not yet famous. He had no laboratory, no institutional position, no graduate students. He had a desk at the Swiss Patent Office and an unusual willingness to follow mathematics wherever it led, regardless of how absurd the destination appeared. The problem Einstein was working through concerned light. Specifically, it concerned a peculiarity in the equations of electromagnetism discovered by James Clerk Maxwell several decades earlier. Maxwell's equations described light as an electromagnetic wave propagating through space at a specific velocity, approximately 2.99792 kilometers per second. The peculiarity was this, that velocity appeared in Maxwell's equations as an absolute constant with no reference whatsoever to the motion of the observer measuring it. This was deeply strange. In ordinary experience, velocities add together in exactly the way you would expect. A ball thrown forward from a moving train travels faster relative to someone standing on the platform than relative to the person throwing it. The thrower's velocity and the ball's velocity combine. Everything moves relative to everything else, and the numbers add together cleanly. Isaac Newton had codified this intuition into a precise mathematical framework 2 centuries earlier, and it worked flawlessly for every phenomenon humans had ever measured. But light refused to cooperate. Experiments in the latter half of the 19th century, most famously the careful interferometer measurements conducted by Albert Michelson and Edward Morley in 1887, consistently found that light traveled at the same velocity, regardless of how the measuring apparatus moved. You could race toward a beam of light at high velocity. The light still approached you at exactly 2.99792 kilometers per second. You could race away from a light source. The light still overtook you at exactly 2.99792 kilometers per second. The velocity of the source or observer seemed to have no effect whatsoever. Light behaved as though it had no interest in Newtonian addition. Einstein chose to take this experimental result seriously, rather than explain it away. He proposed that the constancy of light speed was not a peculiarity to be explained, but a fundamental feature of physical reality, from which everything else must be derived. If light travels at the same velocity for all observers regardless of their motion, he asked, what must be true about space and time for this to be possible? The answer was devastating to intuition, and it was the foundation of everything that followed. If light speed is constant for all observers, then space and time cannot be the fixed, unchanging stage on which events occur that Newton had assumed. They must instead be flexible. They must adjust depending on the relative motion between observers. Two observers moving relative to each other do not simply measure different positions for events. They measure different times, different distances, different sequences, not because one is perceiving incorrectly, but because space and time themselves behave differently for observers in relative motion. Think about what this means concretely. You and a close friend synchronize your watches one morning. She boards a spacecraft and accelerates to a substantial fraction of the speed of light, travels to a distant star, and returns. When she lands, you embrace. You check your watches. They no longer agree. Your watch shows that more time has passed. Her watch shows less. She has aged less than you have. Not because something went wrong with her timepiece, not because she was in suspended animation, but because time itself passed more slowly for her moving body than for yours at rest. This phenomenon, called time dilation, is not theoretical speculation. It has been measured directly. Atomic clocks flown aboard aircraft and returned to Earth tick fewer nanoseconds than identical clocks that remained on the ground. Muons, subatomic particles created in the upper atmosphere by cosmic ray collisions, survive long enough to reach Earth's surface because at the velocities they travel, time passes slowly enough from their perspective to extend their brief existence. The global positioning system that guides navigation on Earth requires constant correction for relativistic time dilation. Without that correction, GPS coordinates would drift by miles within a single day. Every time you use navigation on your phone, you are benefiting from the direct practical application of Einstein's conclusions about moving clocks. But the implications for high-speed travel proved bleak. As an object accelerates toward light speed, something extraordinary happens to the energy required for continued acceleration. In ordinary Newtonian mechanics, accelerating an object requires force proportional to its mass. Double the force, and you double the acceleration. The relationship is linear and straightforward. But special relativity introduces a complication that becomes catastrophic at high velocities. As an object's speed approaches the speed of light, the energy required for each additional increment of velocity does not merely increase, it climbs toward infinity. This is not a statement about the limits of our engines. It is a mathematical fact about the structure of space-time. Picture accelerating a spacecraft from rest to 10% of light speed. The energy cost is enormous but finite. Now accelerate it to 50%. The cost has grown substantially more than 5 times the original because the relationship is not linear at relativistic speeds. Now push it to 90%. The energy bill has grown beyond what any conventional fuel source could supply. At 99%, the cost has become staggering. At 99.9%, the cost is so large that stellar output would be required to push it those last fractions. The mathematics describes a curve that approaches infinity asymptotically. The closer you get to light speed, the steeper the energy requirement becomes. To actually reach the speed of light, not merely to approach it, but to reach it would require infinite energy, a quantity that does not exist anywhere in the observable universe. This asymptotic barrier does not merely make faster than light travel difficult, it makes the very concept of accelerating any massive object to light speed a mathematical impossibility, not an engineering limitation, a definitional one. There is no engine you could build that would overcome this barrier because the barrier is not a property of engines. It is a property of how energy, mass, and velocity relate to each other in the structure of space-time. And then the situation becomes even more severe, because special relativity also demonstrates that faster than light travel would destroy the coherent ordering of cause and effect that makes physics, and indeed any sensible notion of events following from previous events, possible. Consider the concept of simultaneity. In ordinary experience, 2 events either happen at the same time or they do not. This seems like an objective fact about the universe. The explosion happened before the sirens arrived. The dam broke before the flood came. These orderings seem absolute independent of any observer's position or motion. Einstein demonstrated that this intuition is wrong. Events that appear simultaneous to one observer occur at different times for an observer in relative motion. This is not a difference in perception or measurement error. The time ordering of events genuinely depends on the motion of the observer. And for events separated by large spatial distances, what physicists call space-like separated events, different observers can legitimately disagree not just about simultaneity but about which event happened first. Now, consider a signal traveling faster than light. To some observers, such a signal would travel forward in time from sender to receiver, arriving after it was sent. But to other observers in other reference frames, the very same signal would travel backward in time. The receiver would receive the message before the sender sent it. This creates what physicists call a causal paradox. Imagine a precise scenario. You send a faster-than-light message to a colleague on a distant planet. From your reference frame, your message travels forward, in time arriving after you sent it. Your colleague, upon receiving it, immediately sends a reply via another faster-than-light channel. From certain reference frames, this reply travels backward in time. It arrives at Earth before you sent your original message. You now possess information about what your colleague received before you decided to send it. You could choose to not send the original message, but if you do not send it, your colleague cannot reply to something that was never sent. The paradox has no resolution within any coherent framework. It is not a puzzle that clever thinking can untangle. It represents a genuine logical contradiction about the ordering of events. These causal paradoxes are not mere philosophical inconveniences. They would make physics incoherent. Prediction would become impossible. The past would become as uncertain as the future. The ordered sequence of events that allows the universe to have a history and allows beings within it to have knowledge of that history would dissolve. The speed of light therefore functions not merely as a speed limit but as causality's guardian. It ensures that cause always precedes effect for all observers everywhere. Remove it, and you do not merely allow faster ships. You allow the future to influence the past. You allow effects to precede causes. You allow the logical structure of physical law to collapse. This is what Einstein's equations established in 1905. The cosmic speed limit is not a technological barrier awaiting a better engine. It is a structural feature of space-time whose violation would not merely break a record, but threaten to break the coherent ordering of events that makes the universe intelligible. The wall seemed absolute. Infinite energy requirement on one side, causality destruction on the other. Nothing with mass could reach light speed. No signal could exceed it. The stars would remain forever distant, and nothing in physics as understood in 1905 offered any hope of reprieve. Then 11 years later, Einstein changed the problem entirely. In 1916, Einstein completed a second, far more ambitious theoretical framework, where special relativity described how space and time behaved for observers in constant relative motion. This new theory, general relativity, described gravity itself, and in doing so, it introduced a conceptual distinction that would reopen the question of faster-than-light travel in the most unexpected way. The key insight of general relativity is deceptively simple to state and almost impossible to fully absorb. Gravity is not a force, it is curvature. When a massive object like our Sun exists in space, it does not reach out through empty distance and pull on the Earth through some invisible mechanism acting instantaneously across the void. Instead, the mass of the Sun warps the geometry of space and time around it. The shape of space-time itself is altered by the presence of mass, and the Earth moving through this warped geometry follows the straightest possible path available to it, a path that happens to curve around the Sun. The planets are not being pulled, they are coasting through curved terrain. Consider the analogy of a heavy ball resting on a stretched rubber sheet. The ball creates a depression in the sheet. A marble rolled across the sheet near the ball does not travel in a straight line. It curves toward the depression, not because the ball pulls on it, but because the sheet itself is curved, and the marble follows the contour of that curve. Replace the rubber sheet with the fabric of space-time and the marble with any massive object, and you have an approximate picture of how general relativity describes gravity. This geometric picture of gravity has been confirmed to extraordinary precision. Light itself bends around massive objects, as astronomers first confirmed during the solar eclipse of 1919 by observing stars whose light passed near the Sun before reaching Earth. Gravitational waves, literal ripples in the geometry of space-time propagating outward from catastrophic cosmic events, were directly detected in 2015 by the LIGO Observatory, precisely matching general relativistic predictions for the collision of two black holes over 1 billion light-years away. The theory has survived every experimental test thrown at it for over a century. But general relativity introduced something beyond a new description of gravity. It introduced a new way of thinking about space itself. In Newtonian physics, and even in special relativity, space and time provided a fixed backdrop against which events occurred. The stage was permanent. The actors moved across it. The stage itself did nothing. General relativity demolished this picture. Space and time are not a fixed stage. They are a dynamic medium responsive to the matter and energy within them. They can be warped, they can be stretched. And here is the crucial distinction that Alcubierre would eventually exploit. They can expand or contract at rates unconstrained by any speed limit. This last point requires careful attention because it is where everything hinges. Special relativity forbids objects from moving through space faster than light. This constraint applies to motion, to the displacement of objects relative to the space-time background through which they travel. But general relativity introduced a new category of phenomenon, the expansion of space itself. And the expansion of space, it turns out, is subject to no such limitation. The observational evidence for this is already present in the universe around us. Galaxies at the far edges of the observable universe are receding from us at velocities exceeding the speed of light. Not because they are moving through space at superluminal velocities, they are not, but because the space between us and them is expanding. Every moment, new space is being created between those distant galaxies and our own, and the cumulative effect of this expansion over billions of light years produces recession velocities that exceed 299,792 kilometers per second. This does not violate special relativity because nothing is moving through space faster than light. Space itself is growing. The distinction is fundamental. Think of two ants on the surface of a balloon being inflated. Neither ant can walk faster than a certain maximum speed across the balloon's surface. But as the balloon inflates, the distance between the ants increases at whatever rate the balloon expands, regardless of how fast the ants could walk. The ants obey their speed limit. The balloon violates nothing by growing. In the same way, the expansion of the universe carries distant galaxies apart at rates exceeding light speed without any violation of special relativity's constraints. The ants, the galaxies, move through space at ordinary velocities. It is the space itself that expands without limit. This was the door that Einstein's equations opened in 1916 without Einstein himself walking through it. If space can expand or contract at arbitrary rates, carrying matter along with it as a passenger rather than as an object moving through it, then the question becomes unavoidable. Could a region of space be engineered to contract ahead of a spacecraft and expand behind it, creating an effective displacement through the broader universe at faster than light rates, without anything inside that region ever violating the local speed limit? The mathematics, as Alcubierre would discover 78 years later, said yes. Whether the universe agreed was an entirely different matter. Miguel Alcubierre was 30 years old in 1994, a doctoral student in physics at the University of Wales in Cardiff, and he was watching a science fiction television program. This detail matters. Not because science fiction is a reliable guide to physical reality. It is not, but because it illustrates how the most consequential theoretical discoveries sometimes begin, not with a sophisticated experiment or a refined mathematical technique, but with a simple question asked, without the prying inhibitions that formal training can impose. Alcubierre watched a spacecraft on screen travel faster than light and asked himself the question that most physicists had long since learned not to ask seriously. He asked whether Einstein's equations actually permitted anything like this, not in the naive sense of pointing a rocket at a star and accelerating hard enough, but in some deeper, more geometrically creative sense. Whether the structure of general relativity, a theory he understood with professional precision, contained any room whatsoever for effective faster-than-light displacement. He sat down and worked through the mathematics. What emerged was a paper that would be cited thousands of times in the decades that followed, spark an entirely new subdiscipline of theoretical physics, and simultaneously demonstrate that the universe's defenses against superluminal travel were more numerous, more sophisticated, and more deeply embedded in physical law than anyone had previously appreciated. The paper was titled The Warp Drive: Hyperfast Travel Within General Relativity. It is one of the most consequential and most sobering documents in the history of theoretical physics. To understand what Alcubierre found, you must first understand something about how physicists use Einstein's field equations. These equations, the mathematical heart of general relativity, describe a relationship between two quantities. On one side of the equation sits a mathematical object called the Einstein tensor, which encodes the curvature of spacetime at every point. How distances between neighboring points relate to each other, how time flows at different locations, the full geometric character of the spacetime fabric. On the other side sits another mathematical object called the stress-energy tensor, which encodes the distribution of matter and energy. How much mass exists at each location, how energy flows, how pressure distributes through space. Einstein's equation states that these two objects are proportional to each other, linked by constants of nature. The geometry of space-time is determined by the matter and energy within it. Matter curves space. Space tells matter how to move. The two sides of the equation communicate continuously, each shaping the other. For most of the century following Einstein's publication, physicists used these equations in one direction. They started with a known distribution of matter, the mass of a star, the density of a collapsing cloud of gas, and calculated the resulting space-time geometry. This approach produced some of the most extraordinary predictions in scientific history. Karl Schwarzschild derived the geometry of a black hole in 1916 within weeks of Einstein publishing his theory while serving on the Russian front in the First World War. Alexander Friedmann derived solutions describing an expanding universe in 1922. Roy Kerr found the solution for a rotating black hole in 1963, revealing that the geometry of space-time around a spinning mass twists space itself into a vortex. Each of these solutions started with matter and solved for the resulting geometry. Alcubierre reversed the procedure. He began not with a distribution of matter, but with a desired geometry. He asked what space-time configuration would allow a region of flat space to move through the broader universe at arbitrary velocity. He wrote down the mathematical description of that desired geometry, defining exactly how distances and of times would relate to each other in and around this moving region, and then plugged it back into Einstein's equations to solve for what matter distribution would be required to produce it. This approach, sometimes called reverse engineering the metric, is mathematically legitimate. Einstein's equations work equally well in both directions. They are indifferent to which side of the relationship you start from. You can ask what geometry a given matter distribution produces, or you can ask what matter distribution a given geometry requires. The mathematics accepts both questions with equal equanimity. What Alcubierre wanted to create geometrically was this: a region of flat space-time, a bubble essentially in which the geometry is perfectly normal and undistorted, moving through the broader universe at a velocity that could in principle be anything whatsoever. 10 times the speed of light, 1,000 times. The geometry of the bubble's interior would be identical to the geometry of ordinary empty space. An observer inside would experience no unusual forces, no distortion of time, no acceleration of any kind. From their perspective, they would simply be sitting in space. But the bubble containing them would propagate through the universe the way a wave propagates through water. Not by the water molecules moving rapidly from one place to another. Individual water molecules in a wave barely move at all, but by the disturbance itself traveling through the medium. The bubble would not move through space so much as space would carry the bubble forward, compressing ahead and expanding behind in a propagating wave of geometry. The spacecraft inside would never exceed the local speed of light. Relative to the flat space-time immediately surrounding it, the craft would be essentially stationary. Special relativity's constraints would be satisfied completely. Nothing inside the bubble would move through space faster than light. But the bubble, the region of flat space-time itself, would move through the broader universe at whatever velocity the geometry was designed to produce. The distinction is not a technicality. It is the conceptual core of the entire proposal. Imagine you are standing on a moving walkway at an airport. You are not walking. Your feet are still relative to the surface beneath them. But the walkway carries you forward through the terminal at whatever speed it moves. Now imagine a walkway that moves at 1,000 kilometers per second. You remain stationary relative to the surface. You obey every constraint that might apply to your own motion. But the walkway, the medium itself, transports you at velocities your own legs could never achieve. The warp bubble is a moving walkway built from the fabric of space-time itself. Ahead of the bubble, space contracts. The region of space-time between the bubble and its destination is squeezed, compressed, made smaller. A journey of 4 light-years might require crossing only a small amount of compressed space if that space has been sufficiently condensed. The destination does not move toward the bubble in the sense of traveling through space. The intervening space simply becomes less of it. Like folding a map so that 2 distant points touch, the distance between them on the paper has not changed, but the amount of paper you must cross to get from one to the other has collapsed to almost nothing. Behind the bubble, space expands. The region already traversed stretches and elongates, increasing the distance between the bubble's current position and where it started. From outside observers watching, the bubble would see its starting point receding rapidly, not because the bubble is moving away from it at high velocity, but because the space between them is growing. The bubble rides this expanding wake like a surfer on a growing swell. The net effect is that the bubble advances through the universe. its destination approaches, its origin recedes, and the craft inside experiences none of this as motion in any local sense. Alcubierre wrote down the precise mathematical expression for this geometry, a specific form for the space-time metric, the mathematical object that defines distances and time intervals throughout the region that encoded exactly this behavior. The metric was smooth and well-defined everywhere. It satisfied all the mathematical requirements that legitimate solutions to Einstein's equations must satisfy. There were no singularities, no regions where the mathematics became undefined or infinite. The geometry was in every technical sense a valid solution. He then performed the calculation that would define the problem for the next 30 years. He took his metric, inserted it into Einstein's field equations, and solved for the stress-energy tensor. He asked what distribution of matter and energy would a universe need to contain in order for this geometry to exist. The answer came back immediately, clearly, and with devastating precision. The warp bubble requires matter with negative energy density. Not low energy, not zero energy, negative energy, a quantity of energy less than the energy of a perfect vacuum. Something that in ordinary experience and in every laboratory observation in human history does not appear to exist in macroscopic form. Something that curves space-time in the opposite direction from every form of matter and energy we have ever detected. Something that pushes where everything else pulls. To understand why negative energy is required, consider what the geometry demands. The contraction of space ahead of the bubble requires space-time to be curved in a specific direction outward, in a sense expanding away from the bubble's path. Normal matter curves space-time inward toward itself. This is what gravity does. A star, a planet, a grain of sand, all of them pull the surrounding space-time curvature toward their own mass. This inward curvature is what we experience as gravitational attraction. To contract space ahead of the bubble to pull the destination closer requires curvature in the opposite direction, outward, repulsive rather than attractive, and that requires matter with negative energy, matter that pushes rather than pulls, matter whose gravitational effect runs backward relative to everything we have ever observed. This requirement emerged not from any physical assumption Alcubierre made, but from the geometry itself. He asked what geometry he wanted, and the equations told him what matter would be required to produce it. He had not assumed anything unphysical. He had simply asked for the geometry and allowed the mathematics to tell him the price. The price was exotic matter with negative energy density. Consider the magnitude of this problem by working through an analogy at human scale. Imagine you are an engineer tasked with building a bridge across a river. You sketch the design, the span, the arches, the load-bearing structure. Then you calculate what materials you would need. The mathematics of structural engineering tells you precisely how much steel, how much concrete, what tensile strength requirements the materials must meet. If the calculation comes back and tells you the bridge requires materials with negative density materials that have the structural properties of antimatter or somehow push against gravity, you have learned something important. Not about your engineering skills, about the feasibility of the project. Alcubierre had sketched a magnificent geometric bridge across the cosmos. The mathematics of general relativity told him it required materials that do not appear to exist. The natural question is whether negative energy exists anywhere in the universe, even in limited forms. And here the answer is slightly more encouraging than a flat no, but only slightly. Quantum mechanics, the theory governing the behavior of matter and energy at subatomic scales, predicts that certain configurations can produce local regions of negative energy density. The most well-known example is called the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in 1997. The Casimir effect arises from a subtle feature of quantum mechanics. Empty space, what we naively think of as nothing, is not truly empty at the quantum level. The vacuum seethes with fluctuations, with virtual particles continuously appearing and vanishing in pairs, too briefly to be directly observed, but real enough to produce measurable physical effects. These vacuum fluctuations exist across a spectrum of wavelengths, filling space with a kind of quantum noise. Now place two uncharged, perfectly smooth metal plates parallel to each other, separated by a distance smaller than the wavelength of visible light, a gap measured in nanometers. The plates create a boundary condition that restricts which vacuum fluctuations can exist between them. Only fluctuations whose wavelengths fit within the gap can exist in that narrow space. Outside the plates, fluctuations of all wavelengths persist. Inside the gap, certain wavelengths are excluded. The result is that the energy density between the plates is slightly lower than the energy density outside them, lower in fact than the energy density of the ordinary quantum vacuum. The region between the plates has negative energy density relative to the surrounding space. This creates a pressure differential that pushes the plates toward each other, a tiny but measurable attractive force arising purely from quantum vacuum effects. This force has been measured. It is real. It is precisely as quantum mechanics predicts. The Casimir effect represents direct experimental evidence that negative energy density, however small and however localized, is not merely a mathematical abstraction. It genuinely occurs in the physical world. But here is where the gap between what quantum mechanics provides and what Alcubierre's warp bubble requires becomes staggering. The Casimir effect produces negative energy densities on the order of millijoules per cubic meter among the most optimistic estimates. Alcubierre's original calculation for a bubble large enough to contain a spacecraft traveling at a useful fraction of light speed required negative energy equivalent in magnitude to the mass energy of a body, comparable to Jupiter, or in some estimates the entire observable universe. To translate this gap into human terms, the Casimir effect between laboratory plates produces negative energy at scales comparable to the energy of a single bacterium metabolizing a sugar molecule. Alcubierre's warp bubble required negative energy at scales comparable to converting entire planets directly into energy via Einstein's mass energy equivalence. The difference between what exists and what is required spans roughly 30 orders of magnitude, 30 powers of 10, more zeros between those two numbers than there are stars in the Milky Way galaxy. In the decades following Alcubierre's paper, physicists worked to reduce this energy requirement. The efforts were genuine and sometimes clever. Harold White at NASA proposed in 2012 that oscillating the warp bubble, varying its shape dynamically rather than maintaining a fixed geometry, might dramatically reduce the energy requirement. His calculations suggested that with optimal oscillation, the requirement might drop to the equivalent of a few hundred kilograms of exotic matter rather than planetary masses. This was progress in a mathematical sense. The requirement had dropped by factors of billions from the original estimate. It remained utterly beyond anything physics currently permits or suggests will ever be achievable. And the reduction itself rested on assumptions about warp bubble configurations whose stability and physical realizability were never demonstrated. Other researchers examining White's analysis identified concerns about whether the optimized configurations could actually be maintained, whether the oscillations themselves were physically achievable, and whether the energy reduction survived more careful mathematical treatment. The theoretical debate continued as such debates do, with each refinement revealing new complications. There is a deeper problem with negative energy that goes beyond mere quantity. Even if exotic matter with negative energy density could somehow be created or harvested, quantum mechanics imposes strict limits on how it can behave. These limits are known as quantum inequalities, and they were derived in their most precise form by physicists Lawrence Ford and Thomas Roman in a series of papers spanning the 1990s and early 2000s. The quantum inequalities express a principle of conservation that nature enforces rigorously. Any region of negative energy density must be accompanied by a compensating region of positive energy density nearby. The negative energy is not free. It must be borrowed from the quantum vacuum, and the loan must be repaid with interest in the form of positive energy appearing nearby on a timescale inversely proportional to the magnitude of the negative energy produced. The relationship is precise and severe. The more negative energy you attempt to concentrate in a region, the more positive energy must appear nearby, and the more quickly it must appear. Large negative energy densities must be compensated almost instantaneously. Small negative energy densities can persist slightly longer, but but the compensation requirement never disappears. Think of it as a strict accounting system that the universe maintains. You can borrow negative energy from the quantum vacuum, but the debt comes due almost immediately, and the interest rate increases with the loan size. You can never accumulate large quantities of negative energy for any sustained period. The moment you try to build up the reserves you need, the accounting system demands repayment faster than you can use what you borrowed. For a warp bubble requiring sustained negative energy density across a macroscopic region for the duration of an interstellar journey, years, decades, perhaps centuries, the quantum inequalities represent a prohibition that appears as absolute as the original speed limit. Nature will not permit the sustained negative energy budget that the geometry demands. This was the situation as the 20th century ended. The Alcubierre metric existed as a beautiful, rigorous, exact solution to Einstein's field equations. It described a geometry that would achieve effective, faster-than-light travel without violating any constraint of special relativity. The mathematics was clean, the proposal was coherent, and the physical requirements were essentially impossible. The math allowed it. The universe resisted it, but the story did not end there. Because physicists are not easily discouraged, and the Alcubierre metric had opened a door of theoretical inquiry that, once opened, proved impossible to close. If the original proposal faced energy requirements that physics could not supply, perhaps the geometry could be modified. Perhaps a different configuration, a different shape for the bubble, a different profile for the curvature gradients. A different approach to the same fundamental idea might achieve similar results with more tractable requirements. The refinements began almost immediately after the 1994 paper, and they continued for 3 decades. Each refinement addressed one problem, and in doing so revealed new problems lurking beneath. Each solution to one layer of impossibility exposed a deeper layer that had been hidden behind it. What emerged from this sustained theoretical effort was not a path to the stars. It was something more valuable and more sobering. A map of the universe's defenses. A precise inventory of every mechanism by which physical reality refuses to permit what the mathematics in its generosity seems to allow. The warp drive problem is not a problem of insufficient cleverness. It is a window into the architecture of physical law. And the view through that window, the deeper you look, is one of interlocking constraints so deeply embedded in the structure of reality that they begin to resemble not arbitrary restrictions, but necessary features of a universe that permit existence at all. We were only looking at the first layer. There is a place in the physics of the very small, where the universe becomes generous in ways that seem at first glance like loopholes. Quantum mechanics, the theory governing matter and energy at subatomic scales, permits things that classical physics forbids absolutely. Particles tunnel through barriers they classically lack the energy to cross. Objects exist in superpositions of multiple states, simultaneously, until observation forces them to choose. Energy can be borrowed from the vacuum of empty space, conjured briefly from nothing before the debt is called in. The quantum world operates according to rules that seem designed to make classical certainties dissolve at small enough scales. When physicists first understood the Casimir effect, that negative energy density genuinely occurs in the physical world, however briefly and however small, some researchers dared to ask whether this quantum generosity might be scaled. Whether the same principles that produce millijoules of negative energy between laboratory plates might, with sufficient ingenuity, be coaxed into producing the vastly larger quantities that warp drive geometry demands. 3 decades of investigation produced a clear answer. No, not because the attempt was insufficiently clever, not because the experiments were inadequately precise, but because quantum mechanics itself imposes constraints on negative energy that become more severe exactly where the warp drive needs them most. The universe, it turns out, is generous with negative energy in the way a miserly banker is generous, with small loans willing to extend tiny amounts for extremely brief periods, but imposing interest rates that become ruinous the moment you ask for more than pocket change. Understanding why requires a closer look at what negative energy actually is, where it comes from, and why the universe refuses to allow it to accumulate. The quantum vacuum is one of the most counterintuitive concepts in all of physics. Ordinary intuition insists that empty space is empty. Remove all matter, all radiation, all particles of every kind, and what remains should be nothing, a featureless void with zero energy, zero activity, zero content of any kind. This intuition is wrong in a precise, measurable, experimentally confirmed way. Empty space seethes. Quantum mechanics requires that pairs of virtual particles, a particle and its corresponding antiparticle, continuously appear from the vacuum, exist briefly, and then annihilate each other, returning their borrowed energy to the vacuum from which they emerged. These virtual particles are not merely theoretical bookkeeping devices, they produce measurable effects on real observable particles. The LAMs shift a tiny but precisely measured splitting in the energy levels of hydrogen atoms arises partly from the influence of virtual photons, flickering in and out of existence around the electron. The anomalous magnetic moment of the electron measured to 11 decimal places and matching theoretical predictions with extraordinary precision depends on virtual particle effects. The quantum vacuum, the emptiest state achievable in physical reality, is not nothing. It is a seething background of quantum fluctuations with a definite non-zero energy. And this vacuum energy can, under specific physical circumstances, be locally reduced below its average level. When that happens, when the local energy density of the vacuum drops below the average background level, what physicists call negative energy density has been produced. The Casimir effect achieves this through the boundary conditions imposed by two parallel plates. The plates restrict which vacuum fluctuations can exist in the gap between them, reducing the average energy density there below the surrounding vacuum level. The difference is small. For plates separated by 1 nanometer, roughly 10 times the diameter of a hydrogen atom, the negative energy density between them amounts to approximately 1 millijoule per cubic meter. Scale the separation to 10 nanometers, and the effect drops by 5 orders of magnitude to 10 microjoules per cubic meter. The Casimir effect weakens dramatically as the plate separation increases. To produce negative energy at scales useful for a warp bubble, you would need either plates separated by distances smaller than any currently achievable by many orders of magnitude, or some way to stack and amplify the effect across macroscopic volumes. Neither appears remotely feasible, but the quantum inequality constraints close off any hope of the second approach with particular finality. Lawrence Ford of Tufts University began exploring the theoretical limits of negative energy production in the late 1970s and continued this work through the 1990s and 2000s with collaborator Thomas Roman. What they discovered through careful mathematical analysis was that the quantum vacuum operates according to a strict conservation principle for negative energy, a principle that becomes increasingly severe exactly when you most need it to. Relax. The quantum inequalities they derived can be stated in several equivalent ways, but the essential content is this. For any region of space and any time interval, the product of the magnitude of the negative energy density and the square of the time duration over which that negative energy persists cannot exceed a specific bound determined by fundamental constants of nature. Make the negative energy more intense, and it must persist for a shorter time. Allow it to persist longer, and it must be less intense. The product of these two quantities is bounded above by something that does not depend on any engineering parameter. It is fixed by nature. The physical interpretation is unambiguous. Negative energy is borrowed from the quantum vacuum. The loan comes due with interest. The more you borrow, the sooner you must repay. The repayment takes the form of positive energy. An equal or greater positive energy density must appear in the same region within a time determined by the magnitude of the negative energy debt. For a warp bubble requiring sustained negative energy density across a region meters or kilometers in diameter, for a journey lasting years or centuries, the quantum inequalities impose a repayment schedule that renders the enterprise impossible before any engineering begins. To maintain the negative energy gradient required at the bubble boundary for even 1 second, the positive energy compensation that must appear nearby would itself generate gravitational effects that would disrupt the bubble. To maintain it for a year, the required positive energy compensation would dwarf the mass energy of stellar bodies. You cannot store negative energy. You cannot accumulate it. You cannot gradually build up a reserve over time. Every quantum of negative energy conjured from the vacuum is immediately balanced by positive energy elsewhere, and the balancing act occurs on timescales that decrease as the magnitude of negative energy increases. It is as if the universe maintains a running account of all energy transactions and dispatches auditors immediately whenever the balance goes negative, demanding payment before the debt can grow large enough to matter. This is not a technological limitation. There is no clever arrangement of conductors, no exotic configuration of quantum fields, no sophisticated manipulation of boundary conditions that circumvents the quantum inequalities. They emerge from the mathematical structure of quantum field theory itself, from the same foundations that make quantum mechanics work. Violating them would require modifying quantum mechanics at a level that would break the theory's agreement with experimental observations that currently extend to precisions of 1 part in a billion. Ford and Roman were not merely pessimistic theorists imposing unnecessary restrictions. They were mapping the actual terrain of what quantum mechanics permits. The map shows that the territory required for warp drive construction simply does not exist within quantum mechanics, as currently understood. The energy requirement problem motivated the most sustained and creative theoretical effort in warp drive research. Physicists were unwilling to accept that the first barrier encountered was also the final one. If the original Alcubierre configuration demanded impossible quantities of exotic matter, perhaps modified configurations could reduce the requirement to something closer to achievable. In 1999, physicist Chris van den Broek published an analysis examining whether the geometry of the warp bubble could be redesigned to reduce energy requirements. His insight was elegant. The energy cost of the Alcubierre bubble scaled with the volume of the interior, the flat space region being transported, but the flat interior need not be the same size as what external observers see. General relativity permits configurations where the internal geometry of a region differs dramatically from the external geometry. A bubble that appears small from outside could contain an enormous flat interior, like a room that looks like a closet from outside, but contains an auditorium within. Van den Broek proposed constructing a warp bubble whose external diameter was microscopic, perhaps subatomic, while the internal geometry was expanded to contain a macroscopic spacecraft. Because the energy cost scales with external volume rather than internal volume, this configuration could reduce energy requirements by many orders of magnitude. His calculations suggested requirements dropping from stellar masses to masses roughly comparable to a few hundred kilograms. This was a genuine mathematical insight and a genuine reduction in the theoretical energy budget. It was not a solution to the problem. The Van den Broek configuration requires even more extreme space-time curvature than the original Alcubierre geometry. The transition region between the microscopic exterior and the macroscopic interior must accommodate an enormous change in spatial geometry across an infinitesimally small distance. This extreme curvature gradient requires even more concentrated exotic matter at the bubble boundary matter, with even more extreme negative energy density than the original configuration. The total energy requirement is reduced, but the peak energy density required at specific locations is increased dramatically. And peak energy density is exactly what the quantum inequalities constrain. A smaller total energy debt distributed across a smaller region means the repayment schedule becomes even more demanding, not less. The quantum inequality constraints tighten when energy densities increase. Van den Broek's solution traded one form of impossibility for another, redistributing the problem rather than eliminating it. Harold White's 2012 proposal at NASA's Johnson Space Center attracted considerably more public attention, partly because it emerged from an institutional context that suggested practical intent. White examined whether dynamic warp bubbles configurations, where the geometry oscillated at specific frequencies rather than remaining static, might achieve reductions beyond what any static configuration permitted. His numerical calculations suggested that with optimized oscillation parameters, the energy requirement might drop to the equivalent of a few hundred kilograms of exotic matter. The media coverage was enthusiastic. Headlines announced that scientists were working on a real warp drive and had found a way to make it almost feasible. Images circulated of ring-shaped spacecraft designs, based on White's proposed configuration. The impression conveyed was that a breakthrough had occurred, that warp travel had moved from science fiction to science. The physics community responded with considerably more restraint. Several research groups examined White's calculations and identified concerns. The oscillation parameters that produced the dramatic energy reductions required configurations whose stability had not been demonstrated. The numerical methods used contained approximations whose validity at the extreme curvature gradients involved was uncertain. Most importantly, the reduced energy requirements applied to specific optimized configurations that themselves required exotic matter to establish and maintain the calculation of how much exotic matter reduced the energy requirement had not fully accounted for the exotic matter needed to produce the oscillations in the first place. More fundamentally, none of the proposed reductions addressed the quantum inequalities. Reducing the total energy budget does not change the relationship between negative energy density and the timescale over which it can persist. A smaller warp bubble requiring less total exotic matter still requires that exotic matter to be present continuously at the bubble boundary for the duration of the journey. The quantum inequalities forbid this regardless of the total quantity involved. You cannot maintain a negative energy density gradient across any macroscopic region for any macroscopic duration, whether that gradient requires a Jupiter mass or a kilogram mass. The gap between what is needed and what quantum mechanics permits does not close as the energy requirement is reduced. It merely changes character. Originally, the problem was magnitude. The energy required was absurdly impossibly large. After 3 decades of refinement, the problem has partially shifted to duration and stability. Even relatively small quantities of negative energy cannot be maintained long enough or stably enough to function as warp drive fuel. Both problems exist simultaneously. Neither has been resolved. The positive energy proposals represent the most recent chapter in the effort to circumvent the exotic matter requirement, and they deserve careful examination because they have generated the most recent wave of media excitement about warp drives. Several papers published in the 2020s claim to construct warp-like geometries using only positive energy, ordinary matter, and energy of the kind that fills our universe and obeys all known physical constraints. These papers argued that by carefully choosing the geometry and allowing the spacecraft's own mass to contribute to the space-time curvature, warp-like effects could be achieved without requiring anything exotic. The claims require unpacking because they are simultaneously mathematically interesting and physically misleading in ways that matter enormously. The positive energy solutions that have been demonstrated fall into a specific category: subluminal warp geometries. These are configurations that produce warp-like space-time structure for objects traveling below the speed of light. Within this subluminal regime, certain positive energy distributions can indeed produce geometries that superficially resemble Alcubierre's structure, contracting space ahead, expanding space behind, a region of relatively flat space-time carried along by the propagating geometry. If you could build a subluminal warp drive, it might offer some practical advantages over conventional spacecraft, even at below light speed velocities. The occupants would experience no acceleration. The energy expenditure might, in some configurations, be lower than conventional thrust. The geometry might provide some radiation shielding. These are legitimate potential benefits worth investigating. But subluminal warp geometries are categorically different from superluminal ones, and the differences are not minor engineering details. They are fundamental structural features that arise from the way space-time geometry changes character as you approach and cross the light speed boundary. A subluminal warp bubble maintains causal connection between its interior and the broader universe. Light signals can pass from inside the bubble to outside. An observer inside can send signals that reach the bubble boundary and influence what happens there. The physics of communication and control, problematic but not impossible, remain at least theoretically tractable. The interior and exterior exist within the same causal structure. A superluminal warp bubble severs this connection completely and irreversibly. The bubble moves faster than light relative to the surrounding space-time. Light signals from the interior race toward the leading boundary at 29979 2 km per second, but the boundary moves away faster. The signals can never catch up. From the moment the bubble achieves superluminal velocity, its interior becomes causally isolated from everything external to it. Nothing from inside can reach the boundary ahead. No signal, no instruction, no adjustment of any kind. This is not a communication delay. It is causal isolation. The interior of a superluminal warp bubble exists in a pocket of space-time that is, from a causal perspective, completely disconnected from the rest of the universe for the duration of the journey. And the positive energy solutions that work in the subluminal regime do not extend to this superluminal domain. The mathematical structure changes in ways that reintroduce the exotic matter requirement precisely when the bubble attempts to cross into faster-than-light territory. The transition from subluminal to superluminal is not a gradual change that positive energy arrangements might bridge through incremental refinement. It is a qualitative shift in the causal structure of the geometry that redraws the boundary between possible and impossible configurations. Think of it this way. A subluminal warp geometry is like a boat moving through water slower than the waves it creates. The bow wave stays ahead of the boat. The crew can see what is coming. They can steer. They can adjust. The geometry allows communication between the leading edge and the interior. A superluminal geometry is like a boat that has somehow crossed ahead of its own bow wave. The wave causality cannot catch up. What lies ahead is completely unknown and unknowable until it is already inside the bubble. The causal structure has fundamentally changed, not merely become more challenging. The positive energy papers have been cited as breakthroughs in popular science coverage. They represent genuine mathematical contributions to understanding subluminal warp geometries. They do not represent progress toward faster-than-light travel. The distinction matters, and the repeated conflation of these two things in public discussions of warp drive physics reflects a persistent misunderstanding of what the research has actually demonstrated. There is a moment in any sustained encounter with impossibility where the temptation arises to simply declare the problem unsolvable and move on. The warp drive problem has generated this temptation repeatedly over 30 years of investigation. The exotic matter requirement appeared at first glance to be a single decisive barrier. Eliminated, and the path would open. 3 decades of effort have revealed something more complex and more instructive. The exotic matter requirement is not the barrier. It is the first floor of a building that turns out to have many floors each, revealing a new barrier when you reach it. The building does not have a ceiling you can punch through. It has layers that extend deeper than any single theoretical framework can see. This is not a failure of physics or of the physicists who pursued these questions. It is a success of a different kind. Every barrier discovered in warp drive research corresponds to a genuine physical principle whose importance extends far beyond warp drives themselves. The quantum inequalities constraining negative energy describe something fundamental about the relationship between quantum mechanics and space-time structure. The focusing theorems governing how energy curves geodesics reveal essential features of how gravity and matter interact. The causal isolation of superluminal geometries illuminates the deep connection between faster-than-light travel and the preservation of cause and effect. The warp drive problem has been a productive laboratory for discovering what physics actually requires, using an extreme theoretical construction to stress-test the edifice of physical law and map where it will not yield. Alcubierre's metric is an exact solution to Einstein's equations. It describes a coherent geometry. It violates no classical constraint of general relativity, and it requires matter that quantum mechanics will not permit to exist in the necessary form. The gap between mathematical permission and physical existence is not a gap waiting to be bridged. It is a gap whose depth reveals something about the relationship between the theory of gravity and the theory of the quantum that we have not yet fully understood. A complete theory, unifying general relativity and quantum mechanics, quantum gravity, the great unfinished project of theoretical physics, would almost certainly impose additional constraints on exotic space-time configurations that go beyond what either theory alone can express. Every time physicists have united quantum mechanics with another branch of physics, the union has been more restrictive than either theory independently. Quantum electrodynamics is more restrictive than classical electrodynamics. Quantum field theory in curved spacetime is more restrictive than classical general relativity. Quantum gravity should prove no different. The universe appears to defend its speed limit through mechanisms that deepen as you probe further. What lies beneath the exotic matter barrier is not open space waiting for a clever traveler. It is more barrier. The math allows it. The universe resists it. And the resistance, it turns out, has only just begun. Assume for a moment that the exotic matter problem has been solved. This is a significant assumption. It requires setting aside the quantum inequalities, the focusing theorems, the 30 orders of magnitude separating what Casimir plates produce from what warp geometry demands. It requires imagining a physics we do not possess and a technology we cannot conceive, but assume it anyway. Assume that some future civilization or some extraordinarily fortunate discovery has found a way to produce and sustain negative energy density at the scales a warp bubble requires. The bubble forms. The geometry takes shape. Space contracts ahead. Space expands behind. The craft inside sits motionless relative to the flat region surrounding it. The bubble begins to propagate through the broader universe at 10 times the speed of light. 20 times, 100 times, the destination 4 light-years away will be reached in days rather than millennia. Now, ask a simple question. How do you steer? The answer, when you work through the geometry carefully, is that you cannot. Not because the steering mechanism has not been invented yet, not because the engineering is too difficult, but because the causal structure of a superluminal warp bubble makes it geometrically impossible for anyone inside to influence the bubble's trajectory from the moment it achieves faster than light velocity. This is the second layer of the universe's defense, and it operates entirely independently of the exotic matter problem. Solve the energy question completely, and this barrier remains untouched, unchanged, unaffected by any advance in exotic matter physics. It emerges not from what the bubble is made of, but from what the bubble is from the fundamental causal geometry that any superluminal configuration must possess. To understand the control problem, you need to understand what a horizon is in the language of general relativity. The most familiar horizon in physics is the event horizon of a black hole. A black hole's event horizon is the boundary beyond which nothing, not matter, not light, not information of any kind can escape. Objects crossing inward past the horizon are permanently lost to the external universe. No signal they could emit would ever reach an outside observer. The horizon is defined precisely by the causal structure of the space-time geometry. It marks the boundary between regions that can communicate with the external universe and regions that cannot. Black hole event horizons arise because the curvature of space-time near a sufficiently massive object becomes so extreme that the escape velocity, the velocity required to travel outward faster than gravity, pulls inward, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. The horizon is a one-way membrane defined by the geometry itself. A superluminal warp bubble creates a similar structure, but in a different configuration and with different implications. The bubble moves through space faster than light. This means that the leading boundary of the bubble, the region ahead of the spacecraft, where space is contracting, recedes from the interior faster than light. A signal sent from the spacecraft toward that leading boundary travels at 299,792 kilometers per second, but the boundary itself moves away faster. The signal can never reach the leading boundary. More precisely, from the moment the warp bubble achieves superluminal velocity, the interior of the bubble becomes causally disconnected from the leading boundary. No signal, no particle, no influence of any kind originating inside the bubble can ever reach the region ahead of it. The leading boundary is, from the perspective of the bubble interior, forever beyond reach, not far away in the ordinary sense, but unreachable in the absolute causal sense that black hole interiors are unreachable from outside. This creates a profound and irreversible control problem. To steer a warp bubble to change its direction, to accelerate or decelerate, to aim it at a specific destination, you would need to adjust the geometry of the space-time curvature at the bubble boundary. The contraction ahead and the expansion behind are not fixed properties that persist indefinitely once established. They must be actively maintained and shaped by whatever exotic matter configuration produces them. Changing the direction of travel means changing the distribution of exotic matter around the bubble boundary in specific, precisely calculated ways. But the distribution of exotic matter at the leading boundary cannot be influenced by anything inside the bubble. The causal disconnection is complete. An instruction transmitted from the spacecraft to the leading boundary travels at light speed and never arrives. A particle ejected toward the leading boundary accelerates to nearly light speed and still never arrives. There is no physical mechanism by which the bubble interior can communicate with control or influence the leading boundary in any way. The bubble once formed and accelerating to superluminal velocities is on whatever trajectory it began with, forever. Consider what this means in practice. You build your warp bubble somewhere in the vicinity of Earth. You aim it at Proxima Centauri. The bubble achieves superluminal velocity. 4 light-years away, Proxima Centauri's planet, if one exists in a habitable configuration, sits in a specific orbital position at a specific moment. But your journey will take some finite time even at superluminal speeds, and during that time the planet will have moved. Your pre-calculated trajectory aimed at where the planet was, not where it will be when you arrive. You cannot adjust course. You will pass through empty space where the planet was months or years ago. This is already a severe problem for any practical application. It becomes catastrophic when you consider the interstellar medium. Space between the stars is not empty in any absolute sense. It contains approximately 1 hydrogen atom per cubic centimeter on average, along with helium trace, quantities of heavier elements, dust grains ranging from nanometers to micrometers in size, magnetic fields, cosmic rays, streams of charged particles from stellar winds, and occasional denser clouds of gas and dust that represent the raw material for future star formation. None of these pose serious obstacles to conventional spacecraft moving at modest fractions of light speed. At superluminal velocities, the calculus changes entirely. A spacecraft inside a warp bubble is not directly exposed to the interstellar medium in the way a conventional spacecraft would be. The geometry of the bubble contracting space ahead, expanding space behind, interacts with the surrounding matter in ways that remain incompletely understood. But calculations performed in the years following Alcubierre's paper suggest that matter encountered by the leading boundary of the bubble would be energetically processed by the extreme space-time curvature. Particles swept into the contracting region ahead would be accelerated, compressed, and heated to temperatures and densities that generate intense radiation. Over an interstellar journey of several light-years, the accumulation of interstellar material in the region ahead of the bubble could be substantial. When the bubble finally decelerated and dissipated, this accumulated material would be released, a concentrated beam of high-energy particles and radiation aimed precisely at whatever lay in the direction of travel. A spacecraft arriving at Proxima Centauri would arrive bearing a weapon, not by intent, not by design, simply as a consequence of the geometry. The warp bubble is not merely a transportation system. It is unavoidably an energetic interaction with everything in its path. And because the occupants cannot steer, they cannot avoid populated regions, inhabited worlds, or anything else that might lie along their trajectory. The control problem is not one problem. It is a family of related problems, each arising from the same fundamental causal structure, each independently sufficient to render superluminal warp travel untenable, even in the hypothetical universe where exotic matter is freely available. The problem of stopping deserves its own careful examination because it illustrates how deeply the control difficulties penetrate. To decelerate a warp bubble to reduce its velocity from superluminal to subluminal, and eventually to rest, requires changing the space-time geometry around it. The contraction ahead and expansion behind that to maintain superluminal propagation must be gradually modified. The curvature gradients to reduce the exotic matter, configuration adjusted to allow the bubble to slow and eventually dissolve back into flat space-time. All of this requires influencing the leading boundary, which, as established, nothing from inside the bubble can reach. There are 2 conceivable approaches to this problem, and both fail for reasons that become apparent upon examination. The first approach involves pre-programming the warp field to automatically decelerate at the appropriate moment. Rather than relying on real-time instructions from inside the bubble, the exotic matter configuration is set up before departure, with a built-in deceleration sequence that activates at the appropriate time. The bubble accelerates, cruises, decelerates, and stops according to a pre-established schedule without requiring any input from its occupants. This approach transforms the warp drive from a steerable vehicle into a ballistic projectile. You aim it once at the moment of departure, and it travels in a straight line at fixed speed before stopping at a predetermined location. The destination must be known with sufficient precision that the stopping point can be calculated before departure. The trajectory must be free of obstacles for the entire journey. The timing of the deceleration sequence must account for every variable that might affect arrival conditions. For journeys to known planets in well-characterized star systems, these requirements might in principle be met if exotic matter could be produced, if stable warp configurations could be maintained, if every other barrier was somehow overcome. The planet's future position can be calculated from its current orbital parameters. A deceleration sequence can be designed to stop the bubble at the calculated position. Absent any obstacles or unexpected events along the path, the journey might succeed. But consider what this requires. Every decision about the journey, destination, speed, route, timing must be made before departure and cannot be changed afterward. If something unexpected is discovered along the way, no adjustment is possible. If conditions at the destination change during the journey, no response is possible. If the pre-calculated orbital position of the destination planet turns out to be slightly wrong due to a previously unknown gravitational perturbation, the bubble stops in empty space where the planet should be but is not. This is not a ship. It is an arrow shot, blind at a target 4 light-years away. The second approach involves external assistance arranging for some mechanism outside the bubble to modify the geometry and bring it to a stop. If the occupants cannot influence the leading boundary, perhaps someone at the destination could, someone who knows the bubble is arriving and has prepared the appropriate exotic matter configuration to decelerate it from outside. This requires solving the problem of coordinating with someone at a destination 4 or more light-years away. The fastest possible communication with that destination travels at the speed of light, arriving after 4 or more years. Any instructions sent at the moment of departure arrive at the destination after light speed delay. Any response returns after another light speed delay. The total communication time for a round trip exceeds 8 years for Proxima Centauri alone. Meanwhile, the warp bubble traveling at superluminal speed arrives at the destination before any light signal sent at its departure could reach that destination. The bubble arrives before the news of its own departure. The people at the destination cannot prepare for an arrival they have not yet been informed about. There is no way to coordinate an external deceleration mechanism for a vehicle that arrives faster than the signal announcing its departure. The control problem and the stopping problem together reveals something important about the nature of the warp drive proposal. The same properties that make the bubble useful, superluminal propagation, causal isolation of the interior, are precisely the properties that make it uncontrollable. These are not separate design features that clever engineering might decouple. They are consequences of the same underlying causal geometry. You cannot have a superluminal warp bubble that is also steerable and stoppable because the superluminal propagation itself creates the causal structure that prevents steering and stopping. The physics that permits the motion forbids controlling it. Beyond the control problem lies a barrier that operates at an even more fundamental level, one that would exist even if the control problem was somehow resolved, even if the exotic matter problem were solved, even if every engineering obstacle were miraculously overcome. This is the causality problem, and it is in some ways the deepest of all. The causality issue with warp drives is not identical to the causality problem with naive faster-than-light travel, though it is related. In naive faster-than-light travel, an object simply moves through space at superluminal velocity. The causality violation is direct and obvious. The object arrives before a light signal sent from its departure point could reach its destination. The warp drive appears at first glance to sidestep this problem. Nothing inside the bubble moves faster than light relative to local space-time. The occupants and their spacecraft are at rest relative to the flat interior. Special relativity's constraints are locally satisfied at every point. How can causality be violated if nothing is actually moving faster than light? The answer requires thinking carefully about what causality actually means in the context of general relativity, and what happens when you use a warp bubble, not for a single journey, but for a round trip. Imagine a warp bubble traveling from Earth to a point 10 light-years away. Even at modest superluminal speeds, say twice the speed of light, the journey takes 5 years. During those 5 years, a light signal sent from Earth at the moment of departure has only traveled 5 light-years. It has not yet reached the destination. The warp bubble arrives before the light signal sent at its departure reaches the midpoint of the journey. So far, this seems merely fast, not paradoxical. The violation of causality requires a second step. The travelers arrive at their destination 10 light-years from Earth. They board a second warp bubble for the return journey, also traveling at twice the speed of light. 5 years later, they arrive back at Earth. The total journey has taken 10 years. A perfectly ordinary light signal sent from Earth at the moment of departure is just now arriving at the destination. The travelers left 10 years ago, made the round trip, and are home before the slowest possible acknowledgement of their departure has completed even one leg of the journey. From Earth's perspective, they left and returned in 10 years. From the perspective of the space-time geometry, their round trip has created a situation where effects can precede causes. To see why, consider what different observers conclude about the time ordering of events. For a traveler moving relative to Earth at high velocity, approaching the solar system from a specific direction, the relativistic transformation of coordinates can make the traveler's departure from Earth appear to occur after their arrival back home. The causality violation is not an artifact of a single reference frame. It emerges from combining the perspectives of multiple legitimately valid reference frames, each of which measures different time orderings for the events involved. Physicist Richard Gott demonstrated in 1991 that 2 warp bubbles or 2 wormholes or any 2 faster-than-light transport mechanisms used in combination can in principle be arranged to create a closed time-like curve, a path through space-time that loops back to its own past. The math is not speculative. It is a rigorous consequence of combining faster-than-light travel with the relativistic transformation of coordinates. A closed time-like curve is precisely what the name suggests, a path through space-time that returns to its starting point, not just its starting location in space, but its starting moment in time. A traveler following such a path would arrive in their own past. They could interact with their earlier selves. They could prevent events that led to their own journey. The logical contradictions are not subtle, they are absolute. This is not science fiction speculation. This is what the mathematics of superluminal travel implies when applied carefully and completely to all the reference frames involved. The warp drive may avoid direct causality violation on any single trip, but as a technology available for repeated use as any useful transportation system must be, it implies the possibility of building closed time-like curves. And closed time-like curves destroy the coherent ordering of cause and effect that makes physics meaningful. Stephen Hawking took this problem seriously enough to propose in 1992 what he called the chronology protection conjecture. Hawking was then at the height of his intellectual powers, having spent decades investigating the properties of black holes, the nature of space-time singularities, and the intersection of quantum mechanics with general relativity. His 1974 discovery that black holes emit thermal radiation, Hawking radiation, represented perhaps the most important theoretical insight in gravitational physics since Einstein. It emerged from applying quantum field theory to the curved spacetime near a black hole's event horizon, and it revealed deep connections between gravity thermodynamics and quantum mechanics that physicists are still working to fully understand. The chronology protection conjecture emerged from Hawking's examination of space-time configurations that general relativity's classical equations appeared to permit configurations allowing closed time-like curves. He observed a pattern. Every time a physicist constructed a classical spacetime that seemed to allow time loops, quantum mechanical effects near the region where the time loop would form generated catastrophically intense radiation. Vacuum fluctuations that were ordinarily negligible became amplified to destructive intensities, precisely where the causality violation would occur. The mechanism is subtle but important. Near the boundary between the causal past and the causal future, precisely at the point where a closed time-like curve would form, quantum vacuum fluctuations travel through the time loop repeatedly. Each circuit amplifies them. The fluctuations accumulate, building up intensity with each pass through the loop. Before the loop can close completely, the accumulated radiation reaches energies sufficient to destroy the space-time configuration that would have permitted the loop. The geometry collapses before the causality violation occurs. Hawking's conjecture was that this pattern is not coincidental. It reflects a deep principle that the laws of physics conspire through quantum mechanical effects to prevent the formation of time machines, even when classical physics would permit them. The universe protects its own causal structure through a self-reinforcing mechanism operating at the quantum level. The conjecture has never been proven as a mathematical theorem. Deriving it rigorously would require a complete theory of quantum gravity, which we do not possess. But the circumstantial evidence accumulated over 3 decades of investigation is substantial. Every proposed time machine configuration, examined in detail, has revealed quantum instabilities that destroy it. No counterexample has survived careful analysis. Superluminal warp bubbles face identical concerns. Because they can in principle be used to construct closed time-like curves through round trips and multiple bubble systems, the chronology protection mechanism applies. Quantum effects near the warp bubble boundary, particularly near the region where the bubble achieves superluminal velocity and the causal structure changes qualitatively, would generate intense radiation that could destabilize the geometry. Before the causality-violating configuration fully forms, the universe, it appears, does not wait for causality to actually be violated. It destroys the mechanism before the violation can occur. Consider the elegance of this defense. Hawking's chronology protection, if it holds, means that the universe does not need to forbid warp drives through any single definitive prohibition. It merely needs to ensure that any configuration approaching a causality violation generates its own destruction. The defense is automatic, self-activating, triggered precisely by the conditions that would lead to paradox. The universe does not need a policeman to enforce causality. The physics polices itself. This also means that the defense cannot be circumvented through clever engineering. There is no way to screen the warp bubble interior from the quantum fluctuations that accumulate near the boundary. There is no shielding material, no modified geometry, no alternative configuration that prevents the feedback amplification from occurring. The amplification arises from the causal structure itself, from the existence of paths through spacetime that loop back toward their origin. As long as that causal structure exists, the amplification exists. As long as the amplification exists, the geometry is unstable. The chronology protection conjecture, if correct, transforms the causality problem from a logical argument about paradoxes into a physical mechanism that actively destroys superluminal configurations. The paradoxes do not need to be resolved. The universe prevents them from forming. What the fourth layer of constraints reveals, taken together, is a picture of extraordinary sophistication. The exotic matter problem told us that producing the required energy configuration exceeds what quantum mechanics permits. The control and stopping problems tell us that even with perfect exotic matter, a superluminal bubble cannot be steered or halted by its occupants. The causality problem tells us that superluminal travel implies closed time-like curves through round trips. The chronology protection mechanism tells us that quantum effects will destroy any configuration approaching such curves before they fully form. These 4 constraints are independent. Each one alone would be sufficient to prevent practical warp travel. Together they form a defense system of extraordinary depth, each layer operating through different physical mechanisms, each engaging at different scales and through different aspects of physical law. And they connect to each other in ways that deepen upon examination. The causal isolation responsible for the control problem is the same causal structure that creates the causality paradox with round trips. The quantum effects responsible for the chronology protection are the same quantum mechanics that imposes the inequalities on negative energy. The focusing theorems that prevent space contraction using positive energy emerge from the same gravitational principles that generate Hawking radiation near horizons. The universe's defense against faster-than-light travel is not a wall, it is a web. Every thread connects to others. Pull on one and the others tighten. The constraints are not independent accidents of physics. They form a coherent, mutually reinforcing structure that becomes more visible and more formidable the harder you push against any part of it. And we have not yet examined the deepest layer. The barriers encountered so far, exotic matter, control causality, emerge from the intersection of general relativity with quantum mechanics. They represent constraints imposed by our two most successful physical theories working in combination. But there is a third layer of constraint that operates at the level of the geometry itself, independent of quantum mechanics, independent of energy sources, independent of causality protection. It concerns what happens to a warp bubble when it actually moves through space. What happens to the matter and radiation it encounters? What the extreme space-time curvature at the bubble boundary does to the quantum vacuum it passes through, and what the implications of these processes are for anything or anyone that might exist along the path of a superluminal warp bubble crossing the interstellar void. The universe, it turns out, has prepared one more layer of defense, and this one attacks not the bubble's formation, nor its control, nor its causal implications, but the bubble itself from outside continuously for the duration of every journey it attempts to make. The math allows it, the universe resists it, and the resistance is not finished. There is a temperature at the edge of a warp bubble, not a temperature caused by friction with the interstellar medium, not the warmth of starlight absorbed by the hull, not the residual heat of engines working against the void, a temperature arising from the geometry itself, from the extreme curvature of space-time at the boundary between the flat interior and the warped exterior, a temperature that would exist even if the bubble traveled through perfect vacuum, even if no star illuminated it, even if the universe around it were at absolute zero. This temperature is not a minor engineering concern to be managed with better insulation. It arises from the same physics that causes black holes to glow, the same mechanism Stephen Hawking discovered. In 1974, the discovery that transformed our understanding of the relationship between gravity thermodynamics and quantum mechanics. And at the boundary of a superluminal warp bubble, the curvature gradients involved are not merely comparable to those near a black hole's event horizon. They are in some configurations orders of magnitude more extreme. The universe, having already erected barriers of exotic matter, causal isolation, and chronology protection, has prepared one final layer of active defense. This layer does not merely prevent the bubble from forming or control it from being exercised. It attacks the bubble continuously from outside for the duration of every journey with radiation intensities that depend on how fast the bubble travels and how sharply the geometry transitions from flat to warped at its boundary. The faster the bubble moves, the more intense the attack. The math allows it. The universe destroys it. To understand what happens at a warp bubble's boundary, you need to understand why black holes glow. In 1974, Stephen Hawking applied quantum field theory, the mathematical framework describing how quantum particles behave in space-time, to the curved geometry near a black hole's event horizon. The classical picture of a black hole is one of absolute darkness. Nothing escapes. Light cannot climb out of the gravitational well. The event horizon is a perfect one-way membrane. A black hole in a universe at absolute zero would be perfectly black, absorbing everything and emitting nothing. Hawking discovered that the quantum picture is fundamentally different. The quantum vacuum, the seething background of virtual particle pairs continuously appearing and annihilating throughout space, behaves differently near a horizon than it does in flat spacetime. When a virtual particle pair appears near the event horizon, something can happen that cannot happen in ordinary flat space. One particle of the pair falls across the horizon before the pair can annihilate. The other particle, now unable to find its partner, becomes real rather than virtual. It escapes to infinity as genuine radiation. From the perspective of a distant observer, the black hole appears to emit a steady stream of particles with a thermal spectrum, a distribution of energies identical to that of a hot object at a specific temperature. This temperature, now called the Hawking temperature, is inversely proportional to the black hole's mass. Small black holes are hotter, large black holes are cooler. A stellar mass black hole has a Hawking temperature of approximately 100 nanokelvins, extraordinarily cold, far below the cosmic microwave background, undetectable against the background radiation of the universe today. But the effect is real, theoretically robust, and has indirect experimental support through the study of analogous systems in condensed matter physics. Hawking radiation arises wherever space-time geometry creates a horizon, a boundary that separates regions of causal contact from regions of causal isolation. The event horizon of a black hole is one such boundary. The Rindler horizon experienced by an accelerating observer is another. A uniformly accelerating observer perceives the quantum vacuum as having a temperature proportional to their acceleration, an effect called Unruh radiation that is mathematically equivalent to Hawking radiation in different geometric language. A superluminal warp bubble creates precisely such a boundary. The leading edge of the bubble, where space transitions from contracting to flat, constitutes a horizon analogous to a black hole's event horizon. Outside this boundary, the bubble interior is causally inaccessible, exactly as the interior of a black hole is causally inaccessible from outside. The quantum vacuum encountering this geometric transition as the bubble sweeps through space behaves in the same way it behaves near any horizon. Virtual particle pairs are disrupted. One member of each pair finds itself on the wrong side of the causal boundary. The other becomes real and propagates away as radiation. The temperature of this radiation depends on the sharpness of the transition, how rapidly the space-time geometry changes from flat to warped at the bubble boundary. For a black hole, this sharpness is set by the mass and the resulting curvature at the horizon. For a warp bubble, it is set by the design parameters of the exotic matter configuration, how thin the bubble wall is, how steep the curvature gradient at the boundary. Here the situation becomes severe in a very specific way. To reduce the exotic matter energy requirements, the very optimizations that White and Van den Broek and others pursued to make warp drives seem more feasible, you must make the bubble wall thinner and the curvature gradient steeper. A thinner bubble wall with more extreme curvature transitions requires less total exotic matter energy, which was the goal of the optimization. But a thinner wall with steeper curvature transitions also means a sharper horizon, which means a higher Hawking-like temperature, which means more intense radiation produced at the boundary. The optimizations that address the exotic matter problem worsen the radiation problem. Every modification that makes the energy budget more tractable makes the particle production more catastrophic. The two constraints pull in opposite directions, and satisfying one means violating the other more severely. For bubble configurations optimized to minimize exotic matter requirements, the configurations that physicists have spent 3 decades refining calculations suggest that the radiation produced at the bubble boundary would be intense enough to be lethal to any occupants within moments of the bubble, achieving superluminal velocity. The spacecraft inside would not survive its own warp field. This is not a design flaw to be engineered around. It is a consequence of the geometry. The causal structure that creates the horizon is inseparable from the superluminal propagation. Every superluminal warp bubble has a leading edge that constitutes a horizon. Every horizon in the quantum world produces radiation. The radiation intensity increases with the sharpness of the horizon, and the sharpness of the horizon scales with the optimization of the energy budget. The universe has ensured that the more efficient your warp drive becomes, the more effectively it kills you. The interstellar medium compounds this problem in ways that become more troubling upon detailed analysis. The space between stars is not the perfect vacuum of popular imagination. Measured in familiar units, it is extraordinarily sparse, roughly 1 hydrogen atom per cubic centimeter in the diffuse interstellar medium compared to the 27 trillion atoms per cubic centimeter of the air surrounding you. As you read this, by any everyday standard, interstellar space is as close to nothing as matter gets. But a warp bubble crossing interstellar distances encounters this near-nothing continuously for years or decades. The volume swept by the bubble's cross-section over a journey of 4 light-years contains an enormous number of hydrogen atoms, helium nuclei, electrons, cosmic ray particles, photons, and dust grains. Each of these particles interacts with the space-time geometry of the bubble boundary in ways that the extreme curvature makes energetic and complicated. The leading boundary of the bubble, where space contracts, sharply acts on incoming particles, the way an extremely powerful lens acts on light. Particles approaching from ahead find the space around them compressing. Their velocities measured relative to the bubble's reference frame increase as the contracting space amplifies their kinetic energy. They pile up at the boundary, compressed and heated by the geometric transition. Over the course of an interstellar journey, this accumulation becomes substantial. The dust grains and gas atoms swept into the contracting region are not simply pushed aside. The geometry traps them at the leading boundary, compressing them into an increasingly dense and energetic shell of matter surrounding the bubble's forward face. Calculations by physicist Stefano Finazzi and colleagues published in 2009 examined this process in detail and found that the energy concentrations involved could reach extraordinary levels by the end of an interstellar journey. When the bubble finally decelerates and dissipates, when the warp field collapses and the bubble dissolves back into flat spacetime, this accumulated material is released, not gently, not diffusely, but as a concentrated, highly energetic beam directed precisely along the bubble's direction of travel. Aimed, in other words, at whatever lay in the direction of travel, at the destination. The energy in this beam depends on the density of the interstellar medium along the path and the length of the journey. For a journey to Proxima Centauri through typical interstellar medium density, the accumulated energy could reach levels comparable to nuclear weapon yields. For longer journeys through denser regions of the galaxy, through the molecular clouds where new stars form, for instance, the energy release upon arrival could be catastrophic at planetary scales. A warp ship arriving at a destination does not merely arrive. It arrives bearing a weapon. It cannot aim, cannot discharge safely, and cannot discard. The geometry that made the journey possible has spent the entire trip constructing a bomb that detonates at the destination. This effect has no straightforward mitigation. You cannot deflect the incoming particles away from the leading boundary without modifying the geometry. And modifying the geometry means modifying the warp field, which requires influencing the leading boundary, which the occupants cannot do. You cannot discharge the accumulated energy gradually along the journey because the geometry continuously adds more as new interstellar matter is encountered. You cannot choose a path through lower density space because you cannot steer. The same causal isolation that prevents steering also prevents any response to this accumulation problem. The occupants sealed in their causally isolated flat interior cannot know what is building up outside their bubble. They cannot measure it, respond to it, or mitigate it. They will only learn the extent of the damage when the bubble dissipates and the accumulated energy is released around them. The weapons problem is not a peripheral concern or an engineering detail. It is a fundamental consequence of the physics. Any civilization advanced enough to build a functional warp drive would be by that very capability in possession of the most devastating weapons in the history of the cosmos, not by choice, but as an unavoidable byproduct of using the technology at all. Beneath the radiation problem and the interstellar matter problem lies a more fundamental issue that would exist even in perfect vacuum, even with radiation shielding, even if every other concern was somehow addressed. The stability problem. Warp bubble geometries, even when mathematically valid and physically instantiated through appropriate exotic matter distributions, exist in states of extraordinary delicacy. They are not robust configurations that maintain themselves against perturbations. They are precise balances that require every parameter to remain within narrow tolerances to persist at all. Consider what the warp bubble geometry actually is at a physical level. The contracting space ahead and the expanding space behind are produced by specific distributions of exotic matter, maintaining specific energy densities in specific configurations across the bubble boundary. Every point on the boundary must have the right energy density to maintain the right curvature to produce the right geometry. Deviation of any parameter from its required value at any point on the boundary immediately begins distorting the geometry in ways that propagate and amplify. The warp bubble is not like a ball rolling in a valley where small perturbations simply result in the ball oscillating around the lowest point and eventually returning to equilibrium. It is like a ball balanced on top of a hill. The equilibrium exists. The ball can, in principle, remain balanced forever. But any perturbation, however small, grows rather than diminishes. The ball rolls away from the peak, accelerating as it goes. The equilibrium is unstable. Classical general relativity cannot fully analyze the stability of warp bubble configurations because the extreme curvatures involved require quantum gravitational effects that our current theories cannot describe. The geometry near the bubble boundary, where the transition from flat to warped occurs, reaches curvature scales approaching what physicists call the Planck scale, the scale at which quantum gravitational effects become dominant and our current theoretical tools break down entirely. At the Planck scale, space-time itself is expected to have a granular, foamy structure whose properties no existing theory can reliably predict. The smooth, continuous space-time of classical general relativity gives way to something fundamentally different, something that may not admit the precise controlled geometries that warp drive configurations require. Even setting aside Planck scale effects, the thermal fluctuations present in any realistic physical system would constantly perturb the exotic matter distribution, maintaining the warp geometry. Temperature, however, low produces random variations in energy density. These variations translate directly into variations in space-time curvature. The bubble boundary maintained by a precise energy configuration against a background of continuous thermal noise would experience perturbations at every point and every moment. For stable configurations valleys in the energy landscape, these perturbations would average out without destroying the geometry. For unstable configurations balanced at hilltops, they would grow. And warp bubble geometries appear to be profoundly hilltop configurations, sensitive to perturbations in ways that amplify rather than restore. The timescale for instability growth can be estimated even without a full quantum gravitational analysis. For the extreme curvature gradients involved in practical warp configurations, particularly the optimized configurations designed to minimize exotic matter requirements, perturbations at quantum scales would grow to classical significance, within timescales measured in microseconds or less. The bubble would not degrade gracefully. It would catastrophically collapse. The collapse of a warp bubble geometry is not a gentle event. The exotic matter configuration maintaining the curvature would lose coherence. The contracting region ahead and expanding region behind would cease to be precisely maintained. The space-time geometry would transition rapidly from the warp configuration back toward flat space. This transition occurring violently and asymmetrically as different parts of the bubble boundary fail at different rates, would release the energy stored in the curvature gradients as an intense pulse of radiation and gravitational waves. For the occupants, this would not be experienced as the ship slowing down or the warp field fading away. It would be experienced as an instantaneous catastrophic release of energy in the immediate vicinity of the spacecraft. The passengers would not survive, and there is no mechanism for detecting the onset of instability before it becomes irreversible. The causal isolation of the bubble interior means that no measurement inside the bubble can sample the state of the boundary. By the time any effect of instability reaches the interior, the boundary has already failed. There is no warning, there is no abort sequence, there is only the journey and at some unpredictable moment, determined by the interaction between quantum fluctuations and extreme curvature, its end. The stability problem connects to a broader issue that has become increasingly apparent as warp drive research has matured the conflict between the requirements for a functional warp drive and the behavior of physical systems at extreme scales. Every property that makes a warp drive useful also makes it physically fragile. The thinner the bubble wall, the lower the energy requirement, but the steeper the curvature gradient, the sharper the horizon, the more intense the radiation, and the more sensitive to perturbation. The faster the superluminal velocity, the greater the effective distance covered, but the more extreme the geometry, the more intense the Hawking-like radiation, the more catastrophic the accumulation of interstellar material, and the more severe the causal isolation. The optimizations that bring the warp drive closer to feasibility in one dimension push it further from feasibility in others. It is as if the universe has designed the problem to be irreducibly multidimensional, impossible to optimize globally, even when local improvements in individual parameters are achievable. This behavior is not a coincidence. It reflects the fact that the constraints on warp drives are not independent engineering challenges that can be addressed sequentially. They arise from the same underlying physics, and addressing one constraint means moving within a space of physically allowed configurations in ways that inevitably bring other constraints into greater tension. Consider the engineering space available to a hypothetical warp drive designer. You can adjust the bubble radius, the size of the flat interior. You can adjust the wall thickness, how rapidly the geometry transitions from flat to warped. You can adjust the superluminal velocity. You can adjust the shape of the curvature profile at the boundary. You can introduce oscillations, asymmetries, or other structural modifications. Every choice has consequences across multiple constraints simultaneously. A thicker wall reduces radiation intensity, but increases exotic matter requirements. A slower, superluminal velocity reduces radiation and accumulation problems, but extends journey duration. A larger bubble radius provides more comfortable interior space, but dramatically increases energy requirements. The modifications that help with one problem hurt with others, and the relationships are not mild trade-offs, but steep dependencies that make global optimization appear impossible. The engineering space is not a landscape with a distant mountaintop representing the optimal design. It is a landscape with no summit, only different shapes of impossibility separated by valleys of extreme constraint violation. Every direction you move from any starting point leads to worse violation of some barrier. The constraints have no overlap region where all of them are simultaneously satisfied. What the fifth layer of constraints makes clear, when viewed alongside the four before it, is that the universe's resistance to warp drives is not linear. It is not a sequence of hurdles that a sufficiently determined engineering program might clear one by one with the finish line visible in the distance. It is a space of physics, where every apparent solution reveals itself to be a transformation of the problem rather than a resolution of it. Solve the exotic matter problem and the control problem remains. Solve the control problem with pre-programming and the navigation problem emerges. Address the navigation problem with external deceleration assistance, and the communication delay makes that assistance impossible. Design around the communication delay and the radiation from the bubble boundary still attacks the occupants. Shield against the radiation, and the interstellar matter accumulation still builds toward catastrophe. Account for the interstellar matter, and the stability problem still waits to collapse the bubble at any moment. Each layer is real. Each is independent. Each is sufficient alone to prevent practical warp travel. Together they form something that begins to look less like a set of engineering challenges and more like a fundamental message from the structure of physical law. The message is not simply that warp drives are impossible. The message is more subtle and more profound than that. It is that the universe's architecture, the interlocking web of principles governing energy, causality, quantum behavior, and space-time geometry, is so deeply self-consistent that every attempt to extract faster than light travel from it runs into the same deep structure from a different angle. The barriers are not separate inventions. They are facets of the same underlying reality, a reality that permits us to derive the geometry of warp drives with perfect mathematical precision, a reality that permits us to calculate the exact energy configurations they would require, a reality that permits us to understand in extraordinary detail every reason why they cannot be built. The math allows it, the universe resists it, and in the space between those two facts lies something worth examining with great care, not as an engineering problem awaiting a better solution, but as a window into the deepest questions about why the universe is the way it is and what it means that we are the kind of beings who can ask that question and arrive at an answer. The barriers are not the end of the story. They are the beginning of a different, more profound one. There is a particular kind of silence that follows a long investigation into something impossible. Not the silence of defeat, not the silence of a question abandoned, unanswered. Something more textured than either of those. The silence of a question answered so completely from so many independent directions with such convergent clarity that the answer itself becomes a discovery of a different kind from what was originally sought. You set out to find a path. You found instead a map of why no path exists, and the map turns out to be more valuable than any path could have been. Physics has been here before, not with warp drives specifically, but with the experience of encountering fundamental impossibilities that initially appear as failures and eventually reveal themselves as profound truths about the structure of reality. The history of physics is lined with these moments. Each one followed the same arc, an intuition that something should be possible, years or decades of effort to achieve it. The gradual recognition that the impossibility was not accidental but necessary, and then eventually, the understanding that the necessity itself was the discovery that the universe had been teaching something important through every failed attempt. The warp drive belongs to this tradition. Its impossibility is not a dead end. It is a result. Consider what happened when 19th century engineers and physicists attempted to build perpetual motion machines. The desire was entirely rational. A machine that ran forever without consuming fuel would solve every energy problem human civilization faced. The economic and practical incentives for building one were overwhelming, and the attempts were serious. Hundreds of designs were proposed, built, analyzed, and found wanting. Each failure was attributed to friction, to imprecision, to some correctable flaw in the implementation. The next design would do better. The next machine would finally achieve what the previous ones had approached. What emerged from this sustained effort was not a perpetual motion machine. What emerged were the laws of thermodynamics. The first law established that energy cannot be created or destroyed, only converted from one form to another. A perpetual motion machine of the first kind, which produces more energy than it consumes, violates this conservation principle. The second law established that in any closed system entropy, a measure of disorder can only increase or remain constant, never decrease. A perpetual motion machine of the second kind, which extracts useful work from a single heat reservoir without any other effect, violates this principle. These laws were not derived from first principles by theorists sitting in quiet offices. They were extracted from the accumulated evidence of thousands of failed attempts to do something that turned out to be impossible. Every machine that failed to run forever taught physicists something about the relationship between energy, heat, and work. The impossibility was the teacher. The failures were the data. Today, the laws of thermodynamics govern everything from the efficiency limits of engines to the behavior of stars to the ultimate fate of the universe. They underpin chemistry, biology, cosmology, and information theory. They are among the most far-reaching and well-tested principles in all of science, and they were discovered by trying to violate them. The warp drive investigation has followed the same pattern compressed into 3 decades rather than a century. Every barrier encountered the exotic matter requirement, the quantum inequalities, the control impossibilities, the causality constraints, the radiation instabilities, the stability limitations has illuminated a principle extending far beyond warp drives themselves. The quantum inequalities constraining negative energy production are not merely obstacles to warp travel. They are fundamental statements about the relationship between quantum mechanics and space-time geometry, about how quantum fields behave in curved space-time, about the energy conditions that constrain what space-time configurations can exist, about the deep connections between the vacuum structure of the quantum field theory and the large-scale behavior of gravity. Understanding these inequalities required combining quantum mechanics with general relativity in ways that have advanced physicists' understanding of quantum field theory in curved space-time more broadly. The focusing theorems that prevent space contraction using positive energy are not merely engineering constraints. They are mathematical theorems about the behavior of geodesics, the paths that light and matter follow through curved space-time that have applications throughout gravitational physics. They govern the formation of singularities inside black holes. They constrain the behavior of the universe's expansion. They establish fundamental relationships between energy conditions and the global structure of spacetime that appear throughout theoretical physics. The chronology protection investigation that emerged from examining warp bubble causality problems has advanced understanding of the quantum behavior of spacetime near horizons, the nature of quantum vacuum states in time-dependent geometries, and the relationship between causality and unitarity in quantum theories of gravity. These are not peripheral issues. They are central to some of the most important open questions in theoretical physics. Each barrier was a teacher. Each impossibility was a lesson. The warp drive problem has been one of the most productive research programs in theoretical physics, not despite being impossible, but because of it. The relationship between mathematical possibility and physical reality is one of the deepest questions in the philosophy of physics, and the warp drive investigation illuminates it with unusual clarity. General relativity's field equations are in a precise mathematical sense too permissive. They accept solutions that describe configurations physical reality never instantiates. Wormholes, tunnels through spacetime connecting distant regions are exact solutions to Einstein's equations. Closed time-like curves paths through spacetime that loop back to their own past appear in multiple exact solutions. Naked singularities, regions of infinite curvature not hidden behind event horizons, exist as valid solutions under certain conditions. Alcubierre's warp metric is an exact solution. All of these are mathematically rigorous, internally consistent, and satisfy every requirement that the field equations impose. Physical reality appears to contain none of them. This asymmetry is important. The equations do not distinguish between physically realizable solutions and physically impossible ones. They are indifferent. They accept the Schwarzschild solution describing a real black hole and the Alcubierre solution describing an impossible warp bubble with identical mathematical equanimity. Both are solutions. The distinction between them does not appear in the equations themselves. It appears in the additional layers of physical law that the equations do not capture. Quantum mechanics imposes constraints that the classical field equations do not express. The quantum inequalities, the focusing theorems in their quantum forms, the chronology protection mechanism, these emerge from combining quantum field theory with general relativity in ways that go beyond either theory alone. The classical equations are necessary conditions for physical existence. They are not sufficient ones. Something must satisfy them to be physically possible. But satisfying them is not enough. This realization that general relativity is a necessary but not sufficient description of physical reality is itself an important discovery. It tells us that a complete theory of physical reality must incorporate principles beyond what general relativity provides. It must somehow encode the distinction between solutions that can be realized and solutions that cannot. It must contain in its mathematical structure the additional constraints that quantum mechanics and thermodynamics and causality impose. Such a theory would be a theory of quantum gravity, the great unfinished project of theoretical physics, the framework that would unify general relativity's description of spacetime geometry with quantum mechanics' description of matter and energy, producing a single coherent account of physical reality at every scale. We do not have this theory. Every candidate string theory loop, quantum gravity, causal dynamical triangulations, and others remains incomplete, unable to reproduce the full predictions of both general relativity and quantum mechanics in all regimes simultaneously. The problem is extraordinarily difficult, and progress has been slow. But the warp drive investigation tells us something important about what this theory must accomplish. It must explain why general relativity's permissive equations are restricted in practice to configurations that satisfy additional physical principles. It must encode the quantum inequalities, the focusing conditions, the chronology protection, and the stability requirements that prevent warp geometries from being realized. It must derive from deeper principles the difference between mathematical solutions that correspond to physical reality and those that do not. The warp drive is in this sense a probe of quantum gravity, not an experiment that can be performed, but a theoretical test that any candidate theory of quantum gravity must pass. A complete theory should be able to explain from its fundamental principles why warp bubbles cannot exist, not as an additional postulate, but as a consequence of its deepest structure. This is not a modest demand. It is a window into what a fundamental theory of physics must accomplish to be truly fundamental. The pattern of deepening constraints reveals something else about the architecture of physical reality that deserves careful attention. In many areas of physics, constraints on physical systems arise from a small number of fundamental principles. Conservation of energy prevents perpetual motion machines through a single principle of extraordinary generality. The uncertainty principle limits simultaneous knowledge of position and momentum through a single mathematical relationship. The speed of light limit in special relativity emerges from a single postulate about the constancy of light speed combined with the principle of relativity. The constraints on warp drives are different in character. They do not emerge from a single principle of similar generality. They emerge from multiple independent principles, energy conditions, quantum inequalities, causal structure, geometric stability, thermodynamic constraints, each operating through different mechanisms at different scales. The impossibility is overdetermined. It is not one wall but many walls each, independently impassable, all aligned against the same result. This overdetermination is not an accident. It reflects the deep interconnection of the physical principles involved. The same invariance of light speed that creates the speed limit in special relativity also underlies the causal structure that creates the horizon problem in superluminal warp bubbles. The same quantum mechanical vacuum fluctuations that produce the Casimir effect also produce Hawking radiation at bubble boundaries. The same focusing theorems that prevent positive energy from contracting space also govern the formation of singularities inside black holes. The same thermodynamic principles that forbid perpetual motion also constrain the energy budgets of exotic matter configurations. The principles are not independent inventions, each separately forbidding warp drives for unrelated reasons. They are facets of a single coherent structure, the architecture of physical law viewed from different angles. Pull on any one of them, and you feel the tension of all the others through the connections between them. The web is unified, even though its individual strands appear distinct. This unity is reassuring in a deep way, though it is not reassuring for anyone who hoped to build a warp drive. It tells us that physical law is not a collection of arbitrary rules that might have been otherwise, rules that a sufficiently advanced civilization might find ways around through superior cleverness. Physical law is a coherent, self-reinforcing structure where each principle supports the others. The speed limit does not merely happen to coexist with quantum mechanics and thermodynamics. It is continuous with them. It emerges from the same deep structure that they emerge from. Violate it, and you do not merely go fast. You tear the fabric that holds them all together. The impossibility of warp drives is from this perspective evidence of the coherence of physical law. A universe where warp drives were possible would be a universe with fundamentally different relationships between causality, energy, quantum mechanics, and geometry. It would not be our universe with a faster transportation system. It would be an entirely different universe operating according to entirely different principles. There is a particular kind of pride that attaches itself to human ingenuity, and it is not always well calibrated to the difficulty of what it confronts. The history of technology has repeatedly demonstrated that problems once thought fundamental could be solved through sufficient cleverness and resources. The sound barrier, once believed by some to represent an absolute physical limit, turned out to be an aerodynamic engineering challenge. Nuclear energy, once considered purely theoretical, became practical within a decade of sustained effort. The sequencing of the human genome, considered impossibly complex at the outset, was completed ahead of schedule. The examples accumulate. This track record creates a dangerous intuition. It suggests that every barrier examined closely enough turns out to be merely an engineering problem wearing the disguise of a fundamental one, that with sufficient time, talent, and investment, any constraint can be circumvented. That the universe, for all its apparent resistance, eventually yields to determined human inquiry. The warp drive investigation tests this intuition in a precise and consequential way. The barriers to warp drive are not engineering barriers wearing philosophical disguises. They are not phenomena that laboratory experiments have not yet refined sufficiently. They are not theoretical predictions awaiting experimental confirmation that might provide a loophole. They are mathematical consequences of physical theories that have been tested to extraordinary precision across every accessible regime. Special relativity has been verified to precisions of 1 part in a billion through atomic clock experiments, particle accelerator measurements, and gravitational wave timing. General relativity has been confirmed to similar precisions through gravitational wave observations, pulsar timing, black hole imaging, and solar system dynamics. Quantum field theory makes predictions agreeing with experiment to 11 decimal places, the most precisely verified predictions in the history of science. Thermodynamics underlies every aspect of chemistry and biology, and has never been found wanting in any physical system ever examined. The constraints on warp drives emerge from these theories. They are not speculative extrapolations into untested regimes. They reflect the behavior of physical law in regimes we understand extremely well. A civilization that builds a warp drive would need to have found that special relativity was wrong, or that general relativity was wrong, or that quantum mechanics was wrong, or that thermodynamics was wrong, not in minor refinements at the edges of their validity, but in the core predictions that have been verified to the highest precisions achievable. Every GPS satellite tracking your location, every nuclear power plant generating electricity, every laser operating in a laboratory, every particle accelerator probing the structure of matter confirms the theories whose consequences prevent warp travel. The same physics that prevents warp drives also makes our technology work. They are not separate compartments of physical law that might be independently revised. They are aspects of the same coherent structure. You cannot modify one without modifying the other. This is why the warp drive is not simply difficult. It is not merely the hardest engineering project imaginable. It is based on everything physics has established through decades of extraordinarily precise experimentation, a configuration that physical reality excludes. But the impossibility carries an unexpected gift, one that becomes visible only when you stop trying to circumvent it and begin examining what it means. The speed of light is not an arbitrary number. It is not a parameter that happened to come out to 299,792 kilometers per second through some cosmic accident that might have produced a different value in a slightly different universe. The speed of light is the conversion factor between space and time in the structure of space-time, the rate at which causality propagates through the universe. It appears in Maxwell's equations governing electromagnetism. It appears in Einstein's mass-energy equivalence. It appears in quantum mechanics through the relationship between energy and frequency. It appears in the fine structure constant that governs the strength of electromagnetic interactions and therefore the behavior of every atom in existence. Change the speed of light, and you change all of these simultaneously. You change the structure of atoms, and therefore the chemistry of molecules. You change the chemistry of molecules and therefore the biology of living systems. You change the biology of living systems and therefore the conditions for the existence of beings capable of asking about the speed of light. The same constraint that prevents warp drives also makes our existence possible. The rigidity that frustrates our travel ambitions is the rigidity that maintains the stable physical conditions in which stars can burn steadily for billions of years, in which planets can form and persist, in which water can remain liquid, in which carbon can form the complex molecular structures that biological processes require. A universe with a more flexible space-time, one where geometry could be casually manipulated, where the speed of light was merely a suggestion rather than a structural feature, would be a universe in which the precise, reliable physical constants that make complex chemistry possible would not exist. The prison and the home are the same structure. The wall that confines us is the wall that shelters us. The impossibility that prevents our journey to the stars is continuous with the possibility of our existence at all. This does not make the distance to the stars less real or less challenging. It does not transform the profound isolation of our pale blue world in the cosmic dark into something comfortable or acceptable. The stars are genuinely far away. The journey genuinely cannot be shortened through any shortcut physics permits. The loneliness of our position in the universe is genuine, and the warp drive investigation has not alleviated it. What the investigation has done is reveal why that loneliness exists not as an accident of our particular cosmic address or a temporary condition awaiting better technology, but as a consequence of the same deep structure of physical law that made our existence possible in the first place. The distance is not our enemy, it is our context. And understanding that context, understanding with precision and depth why the universe is arranged as it is, why the constraints take the forms they take, why the barriers are as deep as they are, is itself a form of connection to the cosmos that no faster ship could provide. The warp drive investigation ends not with a spacecraft among the stars, but with a clearer understanding of the universe that contains us. And that understanding, hard-won through decades of rigorous theoretical work, represents something the stars themselves do not possess. We are the part of the universe that understands why it is the way it is. That is not nothing. Come back for a moment to the beginning. The light reaching your eyes from Proxima Centauri left that star 4 years, 4 months, and roughly 22 days ago. It crossed 24.9 trillion miles of interstellar space, traveling at 299,792 kilometers per second, without pause, without deviation, without any possibility of going faster. It arrived at your eyes carrying information about conditions at a star you have never visited and will almost certainly never visit. It obeyed every constraint physics imposes on the propagation of light, every rule that the same structure of space-time imposes on warp bubbles and faster-than-light proposals, and every other attempt to circumvent the distance between where we are and where we wish to go. That light is 4 years old. When it left Proxima Centauri, the people who were working on the theoretical refinements to warp drive geometry described in the papers most recently published had not yet written those papers. When it left, the gravitational wave detectors that have since confirmed the precise predictions of general relativity to extraordinary accuracy were still being calibrated. When it left, experiments were still being conducted that would further constrain the quantum inequalities governing negative energy production. In 4 years of travel at the maximum speed the universe permits the light carried, nothing that violated the principles we have spent this entire journey examining. The universe is consistent, extraordinarily, almost oppressively consistent. Everything confirms the same structure from every direction simultaneously. This is what we have found. The journey through warp drive physics has passed through 5 distinct layers of constraint, to each independent, each sufficient alone to prevent what all 5 together make categorically impossible. The first layer, the exotic matter problem. The Alcubierre geometry requires matter, with negative energy density matter that pushes where all known matter pulls. The quantum inequalities derived by Lawrence Ford and Thomas Roman demonstrate that negative energy can only be produced in quantities so small for duration so brief that the requirements of a functional warp bubble exceed what quantum mechanics permits by approximately 30 orders of magnitude. The gap between what exists and what is needed is not a technological challenge. It is a statement about the structure of quantum mechanics itself. The second layer, the control and stopping problems. A superluminal warp bubble creates a causal horizon between its interior and its leading boundary. Nothing from inside can reach the boundary ahead. No signal, no instruction, no physical influence of any kind. The bubble cannot be steered. It cannot be stopped by its occupants. It travels in a straight line at fixed speed until some external mechanism intervenes, a mechanism that cannot be coordinated with because the bubble arrives faster than any signal announcing its departure. The third layer, the causality problem and chronology protection. Superluminal travel, combined with the relativistic transformation of coordinates between different reference frames, implies for round trips the possibility of closed time-like curves, paths through space-time that return to their own BOST. Stephen Hawking's chronology protection conjecture, supported by 3 decades of theoretical investigation, suggests that quantum effects near any space-time configuration approaching a causality violation generate catastrophic radiation that destroys the configuration before the violation can occur. The fourth layer, the boundary radiation problem. Extreme space-time curvature at the bubble boundary produces Hawking-like radiation through the same mechanism that causes black holes to glow. For the optimized bubble configurations designed to minimize exotic matter requirements, The very configurations that represent the best theoretical proposals, radiation intensity at the boundary, would be sufficient to destroy any spacecraft. Inside, within moments of achieving superluminal velocity, the optimizations that address the energy problem worsen the radiation problem. The constraints pull in opposite directions and cannot be simultaneously satisfied. The fifth layer, the interstellar matter, accumulation and stability problems. The leading boundary of the bubble sweeps up interstellar matter and concentrates it into an energetic shell that detonates at the destination. Warp bubble geometries are unstable equilibria that quantum fluctuations would collapse on microsecond timescales. The bubble cannot be maintained for any journey duration. The same geometry that makes it effective makes it fragile beyond any physical system's ability to sustain. 5 layers, 5 independent mechanisms, 5 different aspects of the same underlying coherence of physical law, each one speaking the same message through a different language. The math allows it. The universe does not. What do we do with this? The temptation, understandable and entirely human, is to treat this as a temporary condition, to assume that physics as currently understood is incomplete, which it certainly is, and that future discoveries will reveal the loophole we have not yet found. The history of science contains genuine surprises, genuine overturnings of confident impossibility, claims genuine discoveries that changed what was thought achievable. This temptation should be examined honestly, rather than indulged or dismissed. The impossibilities that history has overturned were in most cases impossibilities rooted in incomplete understanding of phenomena that lay at the edge of what was then experimentally accessible. Heavier-than-air flight was declared impossible by serious scientists who had not fully accounted for the aerodynamic lift generated by appropriately shaped surfaces moving through air at sufficient velocity. The sound barrier was thought by some to represent a fundamental limit before the aerodynamics of transonic and supersonic flight were worked out. These were failures of incomplete knowledge, not consequences of deeply tested fundamental principles. The constraints on warp drives are not of this character. They emerge from the most precisely tested theories in the history of science, applied to well-understood regimes confirmed by experiments extending across many decades and many independent approaches. The uncertainty in these theories is not the uncertainty of incomplete understanding at their core. It is the uncertainty at their boundaries, in regimes we cannot yet access, in the deep structure of quantum gravity, where neither general relativity nor quantum mechanics alone is sufficient. A future discovery in quantum gravity could change the picture. No honest physicist can exclude this possibility with absolute confidence. But such a discovery would not be a refinement of known physics. It would be a revolutionary overturning of principles confirmed to precisions of 1 part in a billion or better. It would require explaining why those confirmations were consistently achieved through centuries of experiment. It would require accounting for why the universe behaves at every accessible scale exactly as the theories whose consequences prevent warp travel predict. The possibility exists. Its probability is not comparable to the probability that better aerodynamics will enable a faster aircraft. And even granting that possibility, granting that some future revolution in understanding might change the picture in ways we cannot currently imagine, we are left with a present in which the stars are genuinely, profoundly, perhaps permanently beyond quick reach. That present is worth inhabiting honestly, rather than denying through premature hope. The genuine future of humanity in space does not require warp drives. It requires something that has always been more difficult to sustain than technological ambition. It requires patience. The nearest star system is 4.2 light-years away. A spacecraft traveling at 1% of the speed of light, a velocity that exceeds anything humanity has achieved by factors of hundreds, but that falls within the range of what near-future propulsion concepts might eventually approach, would reach Proxima Centauri in approximately 420 years. 14 generations of human descendants if they traveled aboard a ship designed to sustain life across centuries. Or perhaps a smaller probe, laser-propelled through concepts like those explored by the Breakthrough Starshot initiative, carrying no passengers but instruments that could transmit data back across the void at light speed. These approaches are not science fiction consolation prizes offered in lieu of the real solution. They are the real solution, constrained only by the enormous practical challenges of engineering, funding, and sustaining civilizational commitment across timescales, longer than most civilizations have endured. They do not violate a single principle of physics. They work within the structure of reality, rather than against it. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object in existence. It has traveled approximately 23 billion kilometers from Earth, roughly 157 times the distance from Earth to the Sun, over nearly 50 years of continuous travel. If aimed at Proxima Centauri, which it is not, it would arrive in approximately 73000 years, traveling at its current velocity of roughly 17 kilometers per second. It carries a golden record containing sounds and images of life on Earth, a message addressed to whoever or whatever might find it in the unimaginable future. Voyager's journey is both humbling and extraordinary. Humbling because 23 billion kilometers achieved over 50 years of flight represents a distance that light crosses in approximately 21 hours. The probe has traveled in 50 years what light covers in less than a single day. The stars are not merely far, they are incomprehensibly far, at any velocity our current technology achieves. Extraordinary because we built it, because it still transmits, because 50 years after its launch, engineers on Earth receive signals from an object beyond the heliopause, the boundary where the sun's influence gives way to the interstellar medium, and use those signals to reconstruct measurements of the plasma environment at the edge of our solar system. Because Voyager's golden record, drifting through interstellar space in the darkness between stars, represents humanity's most literal act of reaching outward toward the cosmos that surrounds us. This is not the warp drive future. It is slower, quieter, more uncertain, and more genuinely connected to what physics permits and what human perseverance can achieve across long timescales. It is real. There is something worth sitting with in the specific character of our cosmic situation described, now not with the vague language of wonder, but with the precise language of physics. We exist on a rocky planet, orbiting a middle-aged star on the trailing edge of a spiral arm of a galaxy containing approximately 300 billion stars. Our galaxy is one of an estimated 2 trillion galaxies in the observable universe. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light-years, larger than the 13.8 billion light-years. Light could travel in the universe's age because of cosmic expansion. Beyond the observable universe, the cosmos continues almost certainly for distances that may be infinite. The portion we can see is not the whole. It is merely the portion from which light has reached us, bounded by the speed of light and the age of the universe working together to define our observational horizon. Within the observable universe, the nearest large galaxy similar in size to our own, the Andromeda Galaxy, lies approximately 2.5 million light-years away. Light that left Andromeda when our ancestors were developing the first stone tools is only now arriving at Earth. We see Andromeda as it was 2.5 million years ago in the deep past, carrying news of a civilization, if one existed there, that is 2.5 million years old by the time it arrives. The galaxy we see in our night sky is not the galaxy that exists now. It is a memory. Warp drives would not have changed this fundamental situation in any ultimate sense. Even a ship capable of crossing 2.5 million light-years at 1,000 times the speed of light would require 2500 years for the journey. The universe's scale mocks even the most optimistic superluminal proposals. The distances are not merely large. They are of a different order than anything human civilization has ever confronted. And yet, within the space we can reach within the local bubble of stars surrounding our sun, within the several thousand light-years that patient multi-generational effort might eventually explore, there are wonders of extraordinary variety. Stars burning in every color from blue-white to deep red, gas giants larger than anything our solar system contains, rogue planets drifting through interstellar space without any star to orbit, heated from within by residual formation, energy, or tidal effects. Binary and trinary star systems, where the sky blazes with multiple suns. stars in their final stages expanding to swallow inner planets, shedding their outer layers in spectacular planetary nebulae, collapsing to neutron stars, where a teaspoon of matter weighs 1 billion tons. These wonders do not require warp drives to reach only time, more time than any individual human life contains, but not more time than our species might aspire to across centuries and millennia of sustained effort. They require the kind of patience that looks beyond immediate return, that invests in futures. It will never personally inhabit, that builds cathedrals whose completion no living member of the construction team will see. Whether human civilization will demonstrate such patience is not a question physics can answer. It is a question about what we choose to be. Return one final time to the question this journey began with. Is faster than light travel possible? You know the answer now. Not as a simple no borrowed from authority, but as a conclusion arrived at through 5 independent lines of argument, each rooted in the most precisely tested physical theories humanity has ever constructed. The exotic matter cannot be produced. The bubble cannot be controlled. The causality it would create would be self-destructive. The radiation at its boundary would be lethal. The geometry would collapse before the journey ended. The answer is no, and the no is as deep as physics goes. But something else has been discovered along the way, something that was not present at the beginning of the journey and is present now in the silence after the answer. The universe that prevents us from reaching the stars in our lifetimes is the same universe that produced the stars. The physical law that forbids us from traveling faster than light is the same physical law that ignites hydrogen into stellar fire, that assembles carbon into molecular complexity, that enables the chemistry of thought to occur in the 100 billion neurons of a human brain. The speed of light is not a barrier erected against us. It is a property of the space-time in which we arose, a property continuous with every property that made our arising possible. We are made of atoms forged in the cores of stars that died before our sun was born. The iron in our blood was synthesized in a stellar explosion that scattered material across light years of space, and some of that material eventually coalesced into the planet we inhabit. We are the universe examining itself through instruments it constructed from its own substance over 4 billion years of biological evolution, using minds shaped by 100,000 years of cultural accumulation, asking questions about structures that existed for billions of years before anything capable of asking about them emerged. The question we asked, can we go faster, has been answered fully. The answer has taught us more than the alternative answer would have. A universe where warp drives worked would be a universe where we could not have derived why they worked, because the stability of physical law required for consistent derivation would not exist. The impossibility and the understanding are inseparable. We cannot cross to the nearest star in a human lifetime through any means physics permits. We have understood with extraordinary precision and depth why this is so. The understanding required building the mathematics of curved spacetime, discovering the quantum nature of the vacuum, measuring gravitational waves from colliding black holes 1 billion light-years away, and tracing the consequences of extreme geometry through 5 independent layers of physical constraints. This understanding did not happen in a laboratory. It happened in the minds of human beings, who looked at equations and followed them wherever they led, even when they led somewhere disappointing, who built theoretical structures of extraordinary beauty that turned out to describe impossibilities with perfect rigor, who found in the mapping of what cannot be done a map of what the universe is. Right now, light is leaving Proxima Centauri. It is crossing the void at 299,792 kilometers per second, obeying every constraint we have spent this journey, examining, carrying information about a star's surface in the form of photons that will travel for 4 years before any of them encounter anything at all. Most of them will pass through the solar system without touching a single atom. A tiny fraction will reach Earth. A smaller fraction still will enter the atmosphere, pass through the lens of a telescope strike, a detector, and become data numbers in a computer, representing the temperature and composition of a star 24.9 trillion miles away. And somewhere, someone will look at those numbers and think about what they mean, about what lies around that star, whether anything orbits it in conditions that could support the chemistry of life, whether the universe has produced in that system what it produced in this one. They will think these thoughts using a brain built from stellar debris in a body maintained by chemistry that obeys the same quantum mechanics that prevents the warp drives they might have wished for. They will think these thoughts because 4 billion years of biological and cultural evolution have produced from the raw material of an unremarkable star's planetary system something capable of wondering about other stars. The light from Proxima Centauri will arrive in 4 years regardless of what we conclude about warp drives. The star will continue burning hydrogen into helium regardless of whether we ever visit it. The universe will continue expanding at accelerating rates, carrying distant galaxies beyond any future reach, indifferent to the ambitions and disappointments of the brief biological structures on one small planet who spent decades trying to find a shortcut. But those brief biological structures discovered something real in their search. They found that the universe is governed by principles deep enough to forbid what they most wanted, consistent enough to forbid it through 5 independent mechanisms simultaneously, and comprehensible enough that they could understand why. They found that the impossibility was not a failure but a fact, not a closed door but a map of the architecture of reality itself. The stars are not unreachable in any absolute sense. They merely require more time than we have. They require patience that outlasts individual lives' commitment, that spans generations' investment in futures that no living person will inhabit. They require the peculiar human capacity to care about things that will not benefit us personally, to build toward horizons we will never reach, to find meaning in the journey, even when the destination lies beyond the span of any single life. That capacity is itself extraordinary. It is itself a kind of light carried forward through generations, arriving eventually somewhere its originators never expected, illuminating things they could not have imagined. The warp drive is impossible. The stars are distant. The universe is vast beyond any number's ability to convey. And right now, on this small planet in this brief moment, something that the universe assembled from its own substance over 14 billion years is looking up at the dark and understanding why the dark is as wide as it is. That is not a small thing. That is perhaps the most extraordinary thing there is.